Grab a seat, and we're going to try to stay on schedule as much as we can. May have to start dancing with that music. So Ashley, is the live stream going? Okay, good. Well, good to have all of you who came. We will have hamburgers and cheeseburgers, so you have to at least stick through lunch to do that. But I know some of you just came for the food. But now I'm Chris Alexander. I think I probably know all of you in this room. Some of you more than I probably want to know. But we appreciate you coming. I'm really excited about this because Ron Holloman is going to be the guy who's going to be up here most of the day. So I get to sit on the back with Chantz and take notes and shake hands and tell stories and all those things. But really appreciate you coming. You know, behind me you can see our lab, and I think a lot of you know Chantz. Chantz during lunch is going to give you a lab tour and kind of show you a lot of the toys that we've accumulated. And you know, when I drive in every day, I have to remind myself that 2 years ago there were just I guess 5 of us that are here now. That we were just kind of getting this thing started, and a lot of times I'll pull in the parking lot and it's hard to find a parking spot. So I tell people most days we're living the American dream and working with a lot of you. So we're having a good time. Obviously, we're focused today on cracks and crack assessment, but we also added repairs because we have some of our friends who like to repair pipelines. And so we're going to talk a little bit about that. I do want to kind of run over the schedule with you a little bit. Those of you who are live streaming, and we've got people literally all over the world. Wendy sent me a list. We got people in the Middle East, somebody from Norway. So it's really neat what technology will allow us to do. There are a few upsides to kind of the COVID shutdown. I think we've all learned how to use a Teams meeting and WebEx and GoTo. Probably 2 years ago, we didn't have any idea how to do that. The live stream thing, I think a lot of churches have had to go to live stream, so that technology's gotten better, and that's actually how we learned how to do this. So anyway, those of you around the world, we welcome you. Because of COVID, we have several of our speakers who weren't able to come, 3 of them, and so they're going to be presenting from Salt Lake City, Houston, and then we're Jason in Edmonton. Yeah, so we've got, some of our presenters are all over the place today as well. So kind of running through the schedule, Ryan and Atul are going to talk to you a lot about kind of what we're doing and on the fracture mechanics side, which is a big focus. And then Sergio Limon, that a lot of you know. Sergio, we're working with him, and we put a joint industry project together looking at using composites to reinforce cracks. So Sergio's going to talk a little bit about that. And then Ken Bagnoli with ExxonMobil is going to be talking today. They've done a lot of work. He's a fracture mechanics guru and going to talk a little bit about kind of the database and some of the work that they've done. And then Edgar Zapata, that a lot of you know, Anderson Associates. If you do any fracture mechanics, and Edgar's over here to my left, is Edgar somebody that you know? And so as we're doing more of that, we're spending a lot of time with him. And I don't know, Edgar, that we've had you presented at a lot of the events that we've had over the years. So I'm excited to hear you speak. He's also a fellow Aggie, which is not necessarily a bad thing. And then Rhett Dotson with ROSEN, who Rhett and I are good friends. We like to give each other a hard time. And so he's going to be presenting via live stream today. And Rhett works with ROSEN, and obviously ROSEN has a lot of advanced ally technologies. And so he's going to be, talking about what they're doing. They're also doing a lot of work with EMAT and crack assessment as well. And then Chantz will have a little break for lunch. Those of you who are here get to enjoy, I think we're doing cheeseburgers today, so you can go home not healthy. And those of you at home, you can eat soup and a peanut butter sandwich, because that's what I usually do when I'm working from home. And then Casey Whalen with CSNRI. We do a lot of work with them, repairing a lot of things. So probably during the lab tour, you'll see some of I know Tim Malley's here, and so we do a lot of work with them. So he's going to talk to you about how they repair using advanced composite materials, and then Jason Skow with integral engineering. He's going to present to us from Edmonton, and he is kind of I'd say he's a probabilistic guru, so he really understands statistics and those kind of things. So kind of before I turn things over to Ryan, I want to kind of give you a high level overview, kind of at ADV, kind of our thought on cracks. And one of the things that's happened, I started working in 1993, which is a long time ago, back when I had all my hair and none of it was gray. I guess kids will do that to you, but kids and work. And so, when we first started doing a lot of this 30 years ago, you had pipelines and you ran tools, but the ILI tools hadn't advanced to where they are today. And so that part of our pipeline industry has really advanced. And there's quite a few ILI companies. They continue to get better. And as an engineer, to me, that's really exciting because I love the technology part of it. But then the other part of it is we're finding things that 30 years ago that we didn't even know that we had in the ground. So as we move forward in time, we have a tremendous responsibility, and you're going to see this from the speakers, that we have a pipeline system that we have to maintain. And there's a lot of, no pun intended, a lot of pressure on us in order to do that. Well, these tools run, they find all this information, and then from that, we've got to make decisions on how to do that. So that's a lot of what we're doing here at ADV. And a common theme that we're seeing, we have 2 or 3 projects going right now. We'll get pipe from the field that the operator has some concerns with it, and run some basic calculations, and it's like, yeah, we probably need to look at this. And then we go to the lab and we start doing pressure cycling and burst testing. And more often than not, because of the operator's willingness to make an additional investment, sometimes the pipe looks better than we really think that it does. But when we do find that there's a problem, I love what we're doing with the repair companies. Okay, so CSNRI, Alan Edwards is here today. Sean Laughlin's here with Pipe Spring. And I don't know if they have any other repair companies, but our repair technologies are also advancing so that when we find there's a legitimate problem, we've tested these repairs to know that they work. And PHMSA, that I think all of us are familiar with, the Pipeline and Hazardous Materials Safety Administration, they work with us in regulating those pipelines. So I think the kind of things we're going to talk about today, and a lot of the things that we're doing from a full-scale testing standpoint, we're trying to drive and bring the technology so that we can make the most informed decision that we can. So anyway, I really appreciate you all being here today. I know we have these events. It's always fun for us to kind of get together. And Ryan, I'm going to turn it over to Ryan. Ryan recently joined us. I'm excited for a lot of reasons. Ryan always has a smile on his face, which I think is really important. Because sometimes as consultants, we like to put a small face, but sometimes it's challenging, especially when there's a lot of pressure to get things done. The other thing is, I'm not a fracture mechanics expert. I've always had a lot of respect for it, but I know Chantz and I are excited to get somebody like Ryan in here who really can help us develop this. So a lot of what you see today in terms of the schedule, Ryan was a driver in that. So Ryan, I'm going to turn it over to you. There you go.
All right, good morning, everyone. So I guess before we get started, I just want to give you a few housekeeping things. For the folks who are here in the back door, there's 1 male restroom downstairs and then 2 upstairs. So, and then about 11:30, we'll break for lunch, as Chris mentioned. All right, so today, as Chris kind of introduced, we're going to be discussing pipeline crack management. And really, before you can talk about how to manage pipelines, you have to understand the subfield known as fracture mechanics, right? And so it's kind of interesting. I imagine if you polled a lot of people in the street, probably 90% of the population has never heard terminology fracture mechanics. It's kind of something that's not thrown around. You don't hear it in the media much. But there's an interesting study that was performed about 40 years ago by the National Bureau of Standards. And at the time, it was kind of interesting. They did a large fracture study, and one of the key points from it was that at the time, 40 years ago, we spent the gross national product was 4% was contributed to fracture issues. So that's pretty significant, considering a large chunk of the population probably has never heard of fracture mechanics before. So why is it important? So I've highlighted a few kind of incidents throughout history, some fairly significant ones. I'm not going to really talk about all of them, but highlight a few. Kind of on your upper left, one of the earliest ones, this occurred almost 100 years ago. And it's kind of an interesting one. It was occurred in Boston. It was at a molasses plant. A big tank basically fractured. It grew, a crack grew and it ruptured. And this happened 100 years ago, right? It killed 11 people, injured 50 people. One of the more significant events also, Liberty ship. This was a World War II ship. Most people have probably seen some images of this. At the time, there were 3 ships that they actually grew cracks, and through fatigue, they actually cracked open, as you can see in the lower left there. And the significance of that particular incident is that it actually was what drove a lot of the development of the fracture mechanics. So a lot of the contemporary models and stuff we're using were that was the initiation for that and led to the development. So, next let's talk about a little bit about what is the fracture mechanics issue with pipelines. So to start with, I want to kind of highlight this chart you see, and kind of what the issue is you see all the kind of in the histogram, the red points, they represent pipeline installation in the United States. And kind of looking from this graph, you can see that 50–60% of the infrastructure was installed pre-1960. So the issue with that is obviously that at the time the steel quality wasn't as good, the quality control wasn't as good at the time, and so you start off with your billet of steel. It had a lot of non-metallic inclusions in it. As you form that steel, what happens is you're actually joining it through a fusion process, right? So it's an autogenous weld, and so you're just applying force and pressure. And when you have some of those, where you have non-metallic inclusions, and you're forming that pipe, what happens is that's how you're pushing the pipe, the material upwards, and you end up with the hook cracks that people in the room here we deal with on a daily basis. You also, especially with the low frequency pipe technology, you see that because we end up with a lot of cold welds or lack of fusion due to stitching issues. And so these are some of the defects that we deal with. So before we really talk about fracture mechanics, I wanted to kind of take a step backwards. And so anyone who's taken a mechanical engineering course, this is kind of one of the earliest concepts you see, is that you have to understand what the applied stress is on your component and then what the strength properties are. And when that applied stress, it exceeds the material strength, that often leads to failure. Now fracture mechanics is a little different. You now introduce the flaw. And so now you have a flaw in the pipe, and with our pipelines, we have internal pressure. That's the applied stress, right? And so the combination of those two, that's what is, you have a driving force to propagate that flaw. So that's trying to propagate that flaw and open it up. You have a competing mechanism, which is your material resistance, right? And that's defined by our fracture toughness. And that's trying to resist that propagation. So basically, it's kind of similar to your strength of materials, but now when your driving force, when it exceeds your material resistance, that's what often leads to fracture. So let me step back a sec. So these three items, the applied stress, the flaw size, and the fracture toughness, is what you really need to know and plug into the fracture models. So now I do want to talk about some of the fracture models that have been historically used within the pipeline industry. And so when I put this together, I kind of thought, I started realizing that this particular subject on the models, you can spend hours talking about this. As a matter of fact, Sergio Limon, who's our next presenter, and Ted Anderson, these are two well-known fracture guys who have supported the pipeline industry for a while. They have entire talks on this. So I wanted to give you some highlights, though, in the time that we have today. So again, speaking of Ted, I grabbed some of these charts from some of his textbooks and talks, but I thought the chart on the upper left kind of described all these different fracture models that the pipeline industry have traditionally used. So a lot of you, some of the more ubiquitous models include the log secant model. So this is on the far left, and the left represents more empirical models. So a lot of these models, a lot of fit to curves, right? And they're not set in very strong physical basis. So what we know about the physics behind the materials don't necessarily reflect in the log secant model. Going to the right, some of the more rigorous and contemporary models include one, API 579. This uses a failure assessment diagram approach, which we'll discuss. And then maybe the newest model of all of these is the PRCI MAT8, and this is Ted's model. And so it's a bit more rigorous, and both of these are set in, they're true to the physics that we know about these materials. So to start with the log secant. So the original log secant, it was developed in about the 1960s. It came about. And it's basically what it showed was that it's unrealistic for shallow flaws. So the modeling error was very great. So they realized they had this issue. And so they developed what's called the modified log secant to try to correct some of those issues, amongst a few others. And when they developed the modified log secant, one of the issues is that the burst pressure, it became somewhat insensitive to Sharpie toughness. And so you saw at lower Sharpie toughness, it behaved, the burst pressure was predicted to be same as at high fracture toughness values. We know physically that's not true. The chart on the lower left, this shows that at lower burst pressures, those burst pressures are controlled by the fracture toughness of your materials. And we did not see that with the modified log secant. And as you get to higher burst pressures, that burst pressure is controlled by your strength properties in your material. I will say though, you know, despite the fact that some of these issues, the original modified log secant, because it did leverage a lot of data that we knew from testing, is that it actually is still very good for predicting burst pressures. But for contemporary pipeline fracture models, again, we have the API 579 approach. And really the benefit of that is you can see this thing called the failure assessment diagram on the left-hand side. And so you have a locus here that you can see that it basically captures the materials from brittle materials all the way to ductile materials and kind of mixed mode in the middle. And anything below that curve is considered safe, and anything that falls outside of that curve would be considered sort of unsafe to operate. And so this is built around a lot of, you know, contemporary ideas. It's derived from a J integral, which is essentially the driving force to propagate that crack. So when you go back to that model, so the Corlast model, that's another, this is Brian Leese's model. You know, it's again, it's kind of between empirical and rigorous, but it is built around contemporary understanding. And of course, the PRCI MAT8 and the 579 models, they're built around J integral and more contemporary fracture mechanics as well. So at the end of the day, you know, I think I would say the 579 model and MAT8, they're both very rigorous, and I would support using either one. 579, obviously, it's built into the standards, so that's one advantage. Where I'm not sure, you know, the MAT8 model, this is a fairly new model that has been introducing to the pipeline industry over the last 5-10 years. And so I think if you're going out to purchase software and things in this area, you'll see a lot of softwares are built around 579, where more of you only find MAT8 and software, I think, that TED's associated with. So now that you kind of have a bit of a feel for the models that are used, let's look at kind of what the assessment for fitness for service or ECA assessment would look like. So first and foremost, you have to determine your starting flaw size. And we saw that in that original triangle that I was showing, right? That the flaw size is very important. So you have to establish that, and you can do it in two ways. You can do it either with a hydrostatic pressure or by leveraging your inspection results. And oftentimes, you can actually use these in parallel to get a feel for the quality of your inspection results. So what you can do here, if you can see this chart here, you leverage your fracture models. In that bottom curve in green, you built these are your fracture curves right here. And so based off your hydrostatic pressure, you can develop those curves, and this is built into a lot of commercial software. So you can determine what your hydrostatic, based off the hydrostatic pressure, you can determine what your largest starting hypothetical flaw size should be. And then the next step is to basically the red curve. You do the same thing, but for your operational pressure. And you can see that this is kind of demonstrates where the margin is very important when you hydrotest. That's, for example, if you were to you had a system that operated at 30% of SMICE, and that maybe for some reason, and I've seen it before, that you only hydrotest to say 55, 60% of SMICE, your margin is very small and you have little time. Your starting size will be large enough that it will take less time for it to grow to failure. So yeah, so then the third step is obviously, this is where you leverage fatigue crack growth models such as Paris's law, and you determine what your starting flaw size is, and you grow it to that critical curve in the red. And I demonstrate that these curves that, I show that there's, that the red curve and the green curve, you see that they're not just one point, and that's because based off your material properties, they can actually shift up and down a bit. So that's one approach to determining what your starting flaw size is, depending on the scenario. The other is obviously to leverage inspection results. The issue with that, obviously, this is an image of a hook crack in some vintage material. You can see that one of the issues is, and as most people know here, that the sizing is quite complex. We'll maybe discuss some of that, what they're doing at ROSEN to try to alleviate that. Once you have a starting flaw size, next thing is to understand what that applied stress is, right? And so you do that by leveraging your SCADA data. And so this is just kind of a hand drawing of what, the pressure time histories typically look like. But if you ever looked at these, they're quite variable. They're not a nice sinusoidal signal. So they're all over the place. So I think this is what area where people understand one of the challenges in this area is that because of the variability and all, when you go and, if you were to try to perform an assessment like this without being familiar with this data, it's difficult because you have to grab the right period of data to represent the cycling going forward to predict the end of life. And so it's challenging you have to be knowledgeable and understanding what that signal looks like and be able to pick up downtimes and things like that. For example, if there was a short downtime and you grab that period of data and kind of model it for the future, it would assume that your pipeline always saw that downtime when you may not want that. And so you have to be, it does take an expert's eye to really interpret that data. And then again, if you've seen this data before, you know that it's quite complex. And it's not something that you would go and try to count the cycle counts by hand. So there is a technique called the rain flow counting procedure. It's proceduralized in ASTM E1049. And basically it's a procedure to simplify that signal, and you would produce a histogram. So you get your delta P. So you set some delta P as say 5, 10, 15 PSI, some reasonable value there. And you tally up all the different times that those number of cycles occurred. And then you can use minor rules to turn that into equivalent number, and the Paris law to do kind of what we were doing on the previous page, where you have your starting flaw size and you grow it to failure based off that cycle counts. So kind of a lot of stuff, and this is leading into our last discussion, Jason Skow from Integral Engineering. So we've been talking a lot kind of deterministic, and I think a lot of people think that way, right? Where we, in a typical assessment with your fracture toughness, you may assume a very lower bounds if you don't have good data. And so, you're very conservative in your fracture toughness. In your crack size, you may add quite a bit of tolerance because we know there are sizing issues with inspection tools. And so you're always being extremely conservative, and then when you plot that on your FAD curve, you can oftentimes overreact. Now, we also know, anyone who's been in the pipeline industry for a while, that there are actually distributions for your material properties. And we know that there's sizing errors. And so we know that these are actually distributions. And so that's what folks like Jason Skow and people are leveraging. And I think this is where people are going in the future. Technique is already used. It's already in civil engineering codes. We see people in, the aviation community using it. Other industries have started leveraging it. Ours is a little more challenging because we don't have a fixed unit. We may be dealing with hundreds of miles of pipeline. But the technique is very similar. It's using the same models, but it's leveraging a Monte Carlo calculator, where it's basically taking these distributions, and I should note that these are just two of the more significant ones, going back to that fracture mechanics diagram where you know that fracture toughness and the flaw size is important. So you're performing millions of simulations, hundreds of thousands, and basically, you know, you can plot those against the FAD to determine what your true probability of failure is. Whereas opposed to if you're just, you know, looking at it from a deterministic viewpoint, you know, you may fall in the FAD, but you have no idea what that probability of failure is. So that will be the theme for some of our later talks today. So this is also kind of leading into some of our talks this morning, is that how do you get those distributions? So a lot of folks, particularly for the fracture toughness distribution, there's a lot of Sharpie impact values. A lot of people in the pipeline industry, they've used Sharpie V-notch specimens. I do want to highlight right here, and I think Edgar Zapata, who's the president of Anderson Associates, who does a lot of this testing, what he'll highlight is that this is actually, it's a high strain rate test, and it measures the amount of energy absorbed. And so what people do, it's not a true measure of fracture toughness. People use correlations to convert that measured energy into a fracture toughness. So you often end up with conservative values. And so Mr. Ken Bagnoli from ExxonMobil, he's developed a large database, and the only database that I know of its kind, where he tested some 700 or so of these compact tension specimens. This is a subsized specimen that's designed to establish fracture toughness. And so he's going to highlight that, and again, that having the database such as that helps develop the curve, these distribution curves that can lead into the probabilistic assessments and also help our deterministic assessments, because there's a time and place for both. So I'll leave you kind of with this chart, and this is a chart that you may see a few times today. It's a well-known chart, but basically it illustrates that there's a geometry effect to your fracture toughness, to establishing that. And so I highlighted that the talk, and a few talks from now, we're going to see the mention of a lot of these compact tension specimens. And this is what's called, it's in high constraint. And so it has a lower fracture toughness. The next specimen called the SCMB, a single edge notch bend. It's I should highlight that the compact tension, even though it's shown it's kind of driven in tension, it's actually a bending specimen as well. Both of these are in high constraint and they have lower fracture toughness. So they'll give you a more conservative value. You'll see also there have been some tests using this single edge notch tension specimen. It's more realistic to the geometry you find in a pipeline. So you start removing some of that conservatism from your fracture toughness. But you'll see that these specimens, they're good for validating some of the results, but they're quite complex, you'll see, as the day goes on to develop. And they're not something that you would necessarily be sending to a lab to test on a regular basis. And so I think this is what leads into kind of what ADV does here is, you know, you don't always have, you know, a full sample, but when you do, it behooves you to test it on a full scale, because you'll never, with a subsized specimen, really mimic the geometry that you see in a full-size specimen. And so that's often what kind of Chris was alluding to earlier, is that, you know, people come in with a number of projects and you've maybe done some small-scale testing and you see some lower fracture toughness and it concerns you. But then when you test it full scale, you see that, you know, that you actually can achieve high burst pressures, much higher than you would assume if you just were relying on small scale material tests. So with that, I'll hand it over to Atul, and he's going to describe a bit more of all of the full scale testing that we do here at ADV.
Mhm. This- So which one is working? This one, this one?
That one's for a live stream.
Okay. Okay, so we'll continue that story. So there's a lot of good things already being discussed. Part of it is the testing aspect of it. Part of it is the probability aspect of it. My presentation is a little bit more on the lighter side. So it's going to hopefully we'll walk through it pretty quickly. But recapping some of the stuff that Ryan talked about, usually in a fracture mechanics assessment, it all starts with detecting your cracks. You have a piece of pipe, you're going in there, you're trying to find out where the cracks are, what the sizes are, what orientation and shape they are. Then you take those shapes, you go in your fracture mechanics, the classic fracture mechanics calculations to determine your crack intensity. So every crack, every flaw, it rises the stress around it in the vicinity. That's what you're trying to find. So you get the crack intensity. That's your, I like to call it as the loading aspect. That's your loading on the pipe. Then the next thing you do is do your material testing, the subscale material testing that Edgar does. You get your fracture mechanics properties, and that defines your capacity side of the equation. And what you do in the last step is you put this together in a failure assessment diagram, FAD, or FADD, as some people call it, failure assessment diagram, or FAD diagram. Anyways, FAD, you put it in FAD, compare the loads to the capacities. If the points are below the failure curve, you're good. If they're above the failure curve, you got to take a closer look at what's happening. So that's your typical assessment approach. What happens there is all these approaches, they are developed in silos. So the guy who is doing the subscale testing is worried about the probabilistic distribution for his subscale testing. The guy who's developing the fracture equations, he is worried about the probabilistic distribution for his fracture equations. And the uncertainties in these individual steps or individual elements starts getting multiplied. Okay, so when you look at the overall picture, it's kind of hard to read, but I'll spell it out. It's garbage in, garbage out. So if you don't have the right inputs to all these fracture mechanics calculations, you are not going to get the right outputs to any of this. And the complexity in some of this will start becoming evident that it is not unusual to find the test results being completely off from what the fracture mechanics calculations are showing you. So what we do is try to supplement whatever is happening on the analytical side with some full-scale test results. That's where we are going to head. So expectations versus reality. So this is a source of everybody's disappointment in life. You expect something, you don't get it, you get disappointed. So that's one crack, one fracture mechanics answer. That's what everyone wants, I got a flaw. I need an inspection guy to come in here. I want him to size it. I want him to tell me exactly what the size and the shape is, so that I can put it in one equation, get one answer. So that's an equivalent of whatever this product is. You get a nice finished product. You hope that that's where you are going to go, but what you get is this. It's a bunch of spare parts. You don't know how these things are going to be put together. Depending on how you put them together, how you interpret the assembly, you are going to get a completely different product. The way it manifests in fracture mechanics is, again, kind of difficult to read. I'm just going to spell it out. It's going to start with, do you really have a crack? If you have a crack, what is the size of it? If you call 3 PAUT guys here and have them size a crack, one of them is going to tell me it's through wall, one of them is going to tell me it's 50%, one of them is going to tell me it's 10%. Well, what is it? No? So you take that, then you start asking questions. Well, is it really both shapes semi-elliptical? Yeah, maybe. Is it really aligned perfectly axial? Yeah, maybe. Is it radially, is the depth perfectly radial? Maybe, maybe not, With all these maybes, that's where you start having confusion. Well, how do I interpret this? The fracture mechanics calculations we are doing are aligned to very specific, very rigid definitions of how the cracks are oriented and how the crack will grow under load. So that's the thing that gives you a completely different reality. Although everything is nicely arranged, there are codes, you follow the codes. What the codes do is help you do something that's more precise, so it prevents people from doing their own little thing in their own manner. It makes everybody do the exact same thing over and over again, but they don't ensure that you have an accurate answer. So you still have this issue about, well, I'm getting a answer, I don't know what it's going to do, and all these little uncertainties in my approach are going to come in there. So this is another version of that story. So the spherical cow. So I'm from India. I used the elephants before. Now I got to use a cow. So this is a famous joke amongst physicists. So there is some town in Netherlands having a milk production problem, and they hire a physicist and ask him to solve it, and he goes and crunches his numbers, whatever the equivalent of API 579 code is, he does that, he does the equation, and he says, I got it, I can fix your milk problem. And then he starts with, well, assume a spherical cow. Well, it doesn't solve the problem. If everybody assumes a spherical cow, they'll get the same answer, but that's not the reality. So a lot of the stuff we do, spherical cow, perfectly elliptical, semi-elliptical boat-shaped crack is the same thing, So that's where we need to acknowledge that the reality that you see, you inspect, you get is different than what the codes are asking you to do. And then there needs to be some kind of bridge between the understanding that you get from those two elements. Okay, so same slide again, just to rehash, but this is the big cover. Sorry, the colors look terrible here. But this is where the value of full-scale testing comes in. So once we understand that there are these variables or variability, uncertainties, all the processes that we do to make these calculations, what testing does, the beauty of the testing is it seems like a daunting task to test a full-scale sample, but what it does is provides you a systemic assessment. You have a piece of pipe, you're not worried about the crack orientation and how it's going and what it's doing and who processed it and all that stuff. What you are getting a system from start to end. You are getting a piece of pipe and you are testing the performance. You are getting an answer that is deterministic at the end of that process. So in essence, what this is doing is a combination of all probabilities in there. It is automatically accounting for the interaction. So if you remember, I mentioned silos. Everything is in silos. Inspection is in silo, and then the analysis is in silo. This combines everything together. You have a piece of pipe, you have a physical test, you have a physical result. It's very tangible. It's repeatable if you want it to be repeatable, and it's usable down the line. So that's where the testing comes in. It is not meant to replace fracture mechanics calculations. It is meant to supplement what you understand. So we'll understand a little bit more on that, how that happens. So with that background, we do a lot of these fracture mechanics testing. We're testing for cracks. What is it that we do when we test for cracks we'll spend a few minutes on that. So it all starts with having full-scale samples, 20-inch, 30-inch, you name it, any size, and you start putting notches in it. So the notches, there's a machine there on the end. I don't know if there's a pointer is working, but is the pointer working? Maybe it is. Okay. Anyways, left side image is an EDM machine. Has a small blade at the bottom. That blade has electrical contact. It's an electrical discharge machining. Cory, I don't know if he's here, but he's very good at it. He's one of our lab leaders. With that kind of machining, you get a notch. So we're going to spend a few minutes at the middle picture right there. So once you get a notch, you are creating a site for crack growth. The notch is not a crack. So we'll repeat that many times in the next few slides. The picture in the center, you see a U-shape, nice shape at the top. And right below the U-shape, at the base of that U, you see a very fine hairline-like crack. The thing at the top, the U-shaped thing, is a notch. It is not a crack. And the thing at the bottom, that's a fine line, is a crack. It is not a notch. How you apply fracture mechanics to this is completely different. that kind of brings about a very critical step in testing for fracture mechanics and full-scale testing, that is the pre-cycling. What pre-cycling does is it grows that crack from the notch. If you do not pre-cycle some of these notches that you're cutting in, you do not have a crack. If you do not have a crack, you're going to be in the gray area of trying to apply fracture mechanics to something that's not a crack. So that's where the essence of pre-cycling comes in. Once you have a pre-cycled specimen, you grow that crack. Once you have the crack, these equations that we are discussing, or the treatments we're discussing, are more applicable to what we are going to do in terms of fracture mechanics. So you get a crack with the pre-cycling. Once they are pre-cycled, you put it in a test pit and you blow them up. Sometimes, sometimes they'll fail during the pre-cycling. So that's the aspect of it. That's the cyclic crack growth. So that's what Ryan talked about, is the fatigue aspect of it. When you want to see the burst performance, you stop the pre-cycling before the sample pops open or bursts open, and then you burst it in a test pit for a sudden rupture or sudden crack growth phenomena. Okay, so that's really what we do. There are different variations. You can measure the crack growth, and you can measure lots of different parameters, but we will skip through the details. We don't need to get into that. And then this happens. Okay, so I'm gonna just use me and Ryan as proxy. So let's say that Ryan does his calculations and shows me that line and says, well, that's your line. If you're above the line, you're in trouble. If you're below the line, you're not in trouble. Then one of us, maybe me or Chantz, will pick up Chantz, for example. Here, Chantz goes in, does the testing, and Chantz says, well, all your points are above the line. So what are you talking about with the line? So that's where this disconnect between full-scale testing and the prediction happens. That is the key in how we interpret the results. So this is where I'm saying that these are not independent branches of fracture mechanics study. If you don't have the line, you're not going to know whether you are testing near baseline, away from baseline, testing conservative side, over conservative side. So you do need the calculations, but to interpret those calculations for physical performance in your lines out in the field, you need the physical testing, the full-scale testing, to make sense of what those calculations are telling you. Are you over? Are you under? Do you need to spend more time figuring out what your cracks are really doing? So that's what happens. And the beauty of this is, once you get those data points out of full-scale testing, it opens a world of possibilities. Sometimes the calculations will tell you it's a spherical cow syndrome. Is based on the assumptions that we are making. It might tell you, well, it's not gonna take even 600 psi. And when you test it, you're gonna find out that the pipe actually takes 1500 psi, not 600. When you do that a few more times, you get a good statistical confidence saying, yes, every time I have this crack in this kind of pipe, I'm getting a 1500 psi. You can actually go back in here, reconstruct the failure assessment diagram, and help you calibrate. It's almost like a calibration process to calibrate towards your pipe, your crack, the type of thing that you're doing. So kind of takes the fracture mechanics understanding and assessment to the next step in how these pipes behave. So that's really introduction to how this thing works. I think we'll go ahead with the rest of the presentation from here. Thank you.
So I think there's time for a few questions. If anyone have some questions for Atul and I before we move forward. Actually, I don't know if there are questions virtually. Question.
Regards to the last graph, and then there was light. Could you go into a little bit about how you would react differently if your test points are above or below the graph?
Yeah. Do you want to talk about your curve here, Atul?
Yeah. You might repeat the question for everybody on one page.
Yes.
Okay. Yeah.
Oh, that,
We got it. We got to have this. Yeah.
Yeah. I'm just gonna hold it. Okay. So interpretation of so question is, if you have a failure assessment diagram that you have done using level 2, level 3, whatever the procedure is, and you go ahead and test a pipe in lab, and there's a data point that comes outside the curve. The interpretation of that is that the pipe is able to sustain more pressure than what the failure assessment diagram is showing you. If the point comes in lower than the failure assessment diagram, or failure curve in the assessment diagram, it means your pipe cannot sustain as much pressure as the failure assessment diagram is showing you. So you are under predicting whatever the flaw characteristics are. So in this case, the way to think about it or extend that understanding is, let's say that these are just two data points. If you continue testing and all of these points start happening right here, there are two ways of interpreting that. Is either your tests are over predicting something, the equations are under predicting something, but you will find out that this, given that this is more of a systemic approach, it's almost an indication that there's something that needs to be updated in the manner that the failure assessment diagram is done. So it either may be a fracture toughness input, it might be a yield strength or a tensile strength input that's slightly different.
Thank you.
Any more questions? Yes.
Ken?
Yeah, I'm wondering if you folks what instrumentation you're using for the crack depth of the gauges and the potential.
Yeah, so that's $1 million question. I mean, literally, if people can accurately predict some of that, keep forgetting that part. Yeah, people will make a lot of money. So there are efforts to.
You want to actually repeat that question?
Yes. Okay. So we'll repeat that question. So when we put the sample in the pit for full-scale testing, we have a notch. Do we track how much the crack is growing, and how do we know that the crack has grown to a certain extent? Is paraphrasing what the question is, right? So we do use routinely clip gauges and weld-on screen gauges that are across the notch. They give us indirect indication of whether the crack is growing. So if you start seeing the clip gauge readings go up exponentially, you know that the crack is growing. The technology still needs a little bit of improvement, some kind of boost. There are things that are in work. We are trying to look at some acoustic emission techniques, some DC potential drop techniques to get in there more accurately, so that we can predict a little bit more precisely where the cracks are. But at this point, it's basically just a clip gauge or a strain gauge that's welded across the notch that helps you indirectly figure out. You don't get a precise estimate of how deep the crack is. If you do a few tests, you can probably make an empirical assumption. But it's a qualitative thing. Whether the crack is growing or not is what we are after.
I guess from the post-mortem.
Yes, that's exactly right. So that's the only other way to figure it out is you break the sample after the test and figure out whether the crack has grown or not. That's where the pain is. You don't want to do that for 10, 15, 20 samples. These tests are very expensive, and that's where the push is for trying to figure out something that's real time that doesn't exist right now. But if it does, that's where we will go eventually.
All right, yeah, that was a good question.
I've had one. Regarding the EDM notches, do you always orient them in different orientations, or what's the methodology for determine how you?
Well, usually I would say, we're most interested in the long stage, so oftentimes we are replacing axially. We've recently started doing a bit of, right in the seam and sometimes off center of the seam and the heat affected zones, as we see that the properties are a bit different there. Sometimes in the base material, so it all depends on kind of what the issue at hand is.
Just to add more colors, that's correct. Most of the time it's axial flaw. It's usually the orientation of your principal load. So you're interested in hoop, then it's axial. If you're interested in axial, then it's circumferential crack. So one of the work that Ahmad is doing, one of our bright young engineers, is trying to get a crack in the girth weld that's circumferential. So it depends on what you're after, but usually the interest is cracks oriented perpendicular to the principal loading direction. So.
All right, any more questions? I think we're kind of at a transition period. Chris, is 9:30 is we're going over to Sergio. All right, so you know, of course, the tool and I will be around, and we can answer more questions about the full-scale testing. After lunch, Chantz and some of the other colleagues at ADB will be taking you around in the back here to folks to show you what the full-scale testing capabilities are. I believe we're even having a sample of an EDM notch sometime. So the folks who are live, you can see that. But now we're going virtual. We're going to speak to Sergio Limon. He's in Salt Lake City.
We want to make sure it's not broken.
Okay. Should I pull out for a second?
You can introduce them.
Okay.
Sergio. I'll get
All right. Yeah, so Sergio, he's going to present some information. So Chris and Sergio, they worked together for quite a while, and over the last year, they've developed a new JIP where they're looking at, you know, these composite materials that have been used in the recent times to repair dents and other features like that, but they're now looking at repairing cracks using composite material. So we have a large JIP that's recently kicked off in the last month or so. And here at ADB, we've been performing some full-size scale tests over the last month or so. So Sergio's going to talk about kind of the theme for that project over the next year. And actually, here we got Sergio on you. Okay. Hey, Sergio.
Hello, Ryan. Welcome. Good morning. Let's test a few things since I am the first of 4 remote presenters. How's the audio coming through? Testing audio. All right, I can see Chris's hand. All right. How about the presentation? Can you see it, Chris? Show me your hand again. All right. All right, I am going to run the presentation now. Okay. Now I can't see you, but hopefully you can see the presentation. All right. Good morning to those of you in Houston, to those of you in Alberta, and maybe the rest of the US and Canada. And good evening to you, the rest of the world. My name is Sergio Limon, as Ryan introduced me. I'm located here in Salt Lake City. I will be presenting an update on this JIP, or Joint Industry Project, that we started last year in trying to understand the performance of composite non-weldable sleeve systems for repairing cracks, lone seam weld defects. So that's what I'm going to present to you today. I'm assuming, Chris and Ryan, that the presentation will be made available to the attendees somehow. And so I hope that will be the case. So I'll be presenting the objectives for the JIP, who's participating in the test matrix and the schedule that we are moving forward with. All right, the objective, well, we have 4 objectives. One is to increase the understanding of what controls fracture of pipes when we have in them some types of cracks or lone seam weld defects, which we generally call them, at least in this presentation, I will refer to them as planar defects. So that's one of the main objectives here. So we won't just be testing and reporting to you cycles to failures, but we'll be looking beyond that. As Ryan and Atul presented, we will look at the science of the fracture mechanics behind that. So the other objective is to help the operators with a crack assessment calculator that will determine what sort of planar defect sizes are candidate for repairing with the systems that we are going to test. I'm telling you right now that not all cracks are candidate to be repaired with composite sleeves. Okay, so this calculator will help the users understand what defect sizes are candidate. This calculator will not tell you how many layers of the repair systems or which direction to apply them. That's not what this calculator is going to do. Essentially, this is a fracture mechanics based calculator that predicts failure for a certain crack size. It is not to tell you how many layers or how to design the repair. Okay, that have to be dealt with the manufacturers of the repair system themselves. Of course, we're going to test the performance of the repair systems themselves, and then we want to involve the regulators. So we are engaged already with at least PHMSA initially. Chris Hoydell and Steve Nanny are the ones who are reaching out and keep him appraised of what the progress of this project. Okay, so this is a good question. So why are we doing this? Can cracks be repaired with composite sleeves? Well, first of all, I think we have to go into the question of what does it mean to repair a crack? Is it to really stop it from leading a pipeline to fail by leak or by rupture, or is it to stop it basically to becoming a critical size? So you go out in the field, you find a defect that looks like crack or like a lack of fusion. So who determines what's a critical defect, and how is that determined? And so we like I said, not all cracks will be candidate to repair with composite sleeve. So we need to find ways to determine what's a candidate defect. Since critical defects generally is defined those that are going or close to fail at some operating pressure or some safety factor. So generally, there is no standard way of determining when a crack is critical. Operators have their own ways sometimes to determine what that size is and conditions lead to a repair. So you still have to use type B sleeves in certain occasions, composite compression sleeves, metallics that you weld on the pipe, like Petro sleeve is one of them, or cutout. So each of those have a place in the options that operators have for determining what's the most appropriate repair for the crack, for the pipe conditions, and so on. So what we're trying to explore is what crack sizes, what types of defects are candidate for repairing with composite sleeves. And so how about subcritical defects? Okay, so not all cracks are injurious to the pipe. Okay, so how is that determined? Which cracks are more candidates to repair with a compression sleeve than a type B sleeve, or potentially with this sort of a composite sleeve system that we're trying to test? Because not all of them need to be repaired. Not all cracks that are reported from a crack tool are actually, and are found in the field. They're not injurious to the pipe. Just like us humans, we all have imperfections, but not all of those imperfections need repair. Just like people, not all people will need a COVID vaccine. I actually got the virus over the holidays, and fortunately for me, I was fine. Didn't have much of an issue. So do all people need COVID vaccine? Do all cracks need repaired? So those are the things that need to be addressed, and that's part of our scope here for this GIP. So this is not the first time that composite sleeves have been studied or tested to see if they can repair cracks in pipelines. So I want to acknowledge a few of them. This is one of the this is the Agility pipeline in Australia, 34-inch natural gas. They had stress corrosion cracking, and at that time they used clock springs. They used a lot of the Petro sleeves. They were challenged to handle. They're fairly, for this diameter of pipe, they're fairly large and heavy. And so Agility wanted to see other options for more of a moderate to less severe cracks, as they were able to determine the severity of those cracks. So they tried this out, and they actually proved that for certain crack sizes and conditions, this proved to be a good option for them. Another study that has been already completed is the test that Chris did for Boardwalk. This is for a specific pre-1970W pipe, an ethylene pipeline. And at that time, they tested only one system, two systems, the carbon-based Atlas and the composite sleeve. This is sort of a hybrid metal and e-glass system. And the last one is this test done by Colton Sheets at Stress Engineering for a number of high-frequency ERW and low-frequency, in which they use a number of carbon fiber-based composite sleeves. And you can look at those references for additional details. So it's not the first time that we have tried to see the performance of composite sleeve for repairing cracks in pipelines. So what type of defects are we targeting? Well, we have for sure pipe body cracks, like you will see here. Hopefully you can see my laser. And so you have this sort of starting defect sizes. In this case, is a colony of cracks, and And in the body of the pipe, here's a view from the top of the pipe before fracture. So those are one type of defects that we're trying to target. And the other group of defects are seam weld defects, like lack of fusion, right in the bond line of, let's say, per 1970 W or EFW type seam, or selective seam corrosion, as shown here at the bottom. Now, the sizes, like I said, what you see here are very severe, very large. Potentially, those are not candidates for repairing with a composite sleeve. So we're trying to find the sizes that are candidates, and I'll show you a few. So we have the industry standards. We know ASME 31.4 and 31.8, and even the Canadian Z662 offer tables that tells you what sizes of cracks and types should be repaired, and they list the types of repair appropriate or allowed for those types and sizes of defects. But those are default answers, okay? Each of those standards, they list that you can use another type of repair as long as that repair system has been demonstrated through engineering analysis and testing that is actually appropriate to be used in that type of defect in pipe operations. PHMSA in the US, the federal regulators, has essentially the same clause that says that as long as the repair system has been demonstrated that is adequate for that type of defect and conditions, that can be used. It may require a special case filing with PHMSA if you're using a system that is not already in some of the industry standards. Okay, so as Ryan and Atul mentioned, one of the differences in our JIP test program from the previous one is that we're going to focus more on the material science and the fracture mechanics aspects of what causes a crack to grow. And eventually we want to demonstrate that how the cracks were arrested or their growth was reduced by the composite repair system. So we'll focus on fracture mechanics principles, and particularly what can make a crack grow, which is essentially answering the question, what controls fracture in a pipeline that has cracks or lack of fusions? So if we understand the physics, the science behind that, then we'll be able to target, okay, what are we modeling, what do we expect from the repair systems to stop the crack growth? And here's the well-known triangle in fracture mechanics. Okay, the stress analysis, the flaw characteristics, and the material properties all affect the fracture behavior, in which we can use to predict the failure pressure of pipes with defects. So we will look more in detail at the what can cause a stable crack or subcritical crack to become stable, and generally it will be fatigue. Sustained load, like the MAOP, of course, is always there. But fatigue loading is generally what will drive the growth of subcritical stable cracks to failure. So we will obviously report the cycles to failure, and that's an important component. But we know it's not sufficient. It doesn't tell us the whole story. We have to look into the metallurgical analysis at the science level to see how the crack grows as or it doesn't grow when it's repaired, but the system that we are going to test in this program. So for instance, here's again that picture I showed earlier. So you have this existing cracks is essentially, in this case, is a colony of cracks. The black scale is the corrosion defects there. They're actually often difficult to remove. They're very attached to the surface. So if you have a crack column that looks like this, so eventually the cracks will coalesce, with time, sustained loads, the environment, in this case, because it's SEC and potentially fatigue loading, they will coalesce and form one single colony, okay? And then what we will look then is what can cause that joint or coalesced group of cracks to grow in a stable manner. So it may grow to this particular size, and through with time and loading, it may grow a little more, and then eventually, in this case, actually grow through wall. So the failure mode was leak, okay? And so what we're trying to find out in the test study that we are conducting is we will look at how the initial crack started, okay? And then any potential growth and coalescence, and any growth that ideally what we want is the composite sleeve to show and stop the growth of the crack either at this level or some level before it becomes critical, okay? And that's what we were looking, and for that we need to open up the fracture surfaces and use metallurgical techniques to help us find that progress in the crack growth. And of course, as I mentioned before, we're also keeping the regulators appraised from the beginning. Okay, that's what's different from our program to what's been done before. Okay, so like I said, not all cracks will be not all cracks are candidates right now. Not all cracks are candidates to be repaired with composite sleeve. We told that to the many times to the repair manufacturers. Don't be promoting composite sleeve openly out in the industry, okay? Because not all cracks are candidates to be repaired with composite sleeve. So we need to find ways to help the users determine what are candidates. So this is a crack depth over length chart, is the critical crack size, sentence plot. There's equal cracks charts for corrosion and some of the defects. This is a common way that we use to determine. So essentially, let's say here this red curve then represents crack sizes that are expected to fail at MAOP. Right on the curve or above will fail at MAOP. Anything below that red curve will survive at MAOP. So if you pressure test the line to some safety factor, let's say 1.39, then that represents the blue curve here. Again, any curves on the blue line will fail at MAOP and above. Okay, but any sizes below that blue curve will survive the pressure test. So that's one common way to utilize this sort of curves. And you just need to select a model to help you determine those, which Ryan, mentioned some of them: NG18, Coreless, API 579, MAT8, and similar models. So the way it works out then is when you go on the field and find cracks, you're confident with the NDE technique used in the field, and they're reported to you right on the curve, or sometimes above the curve, but they haven't failed because the safety factors applied to the curve. Then those are considered definitely critical, near critical. So therefore, you will have to repair it with a type B or cut them out. Okay. Then there is a zone, an area here between that MAOP and some safety factor. That's can be decided, by the operator, 1.1, 1.25, 1.9, or any other number. So any cracks that are found in the field and the fall, let's say between the two lines that are called, I can call them significant, okay? So those can be possibly repaired with a type B, a composite metallic sleeve, like a Petro sleeve or similar, or cut out. And so what we're looking at is what defects are candidates to repair with this sort of non-weldable composite sleeves. And we think they will be somewhere, around the safety factor line that operators will use, okay? And so it will be much smaller crack sizes. All right, so here's the calculator that we're developing. So this is the user interface. They enter the material properties, in this section, the pipe properties, and then the crack sizes, and they can then determine a curve that looks like this, which I just went through. So you can calculate, this is actually, I did that for a 12-inch to 50 X46. This is basically one of the pipes we are going to test in this GIP program. And so the calculator will spill out this sort of curves. Now the user will have a good idea, crack size, depth over the length. They will have an idea if the defects are candidate depending on the safety factors that are used. Another output of this calculator will be, because often the user will not have the fracture toughness for that pipeline of interest where the crack is found in the field. And again, Ryan and Atul mentioned this. It's often that's the case. So this is a plot of the predicted failure pressure with a fracture toughness. When you don't know what the toughness is, by the way, these are not your common Sharpie units. These are more fracture mechanics based units called a KJMAT in case of square inch. So here I have 3 crack sizes, all the same length, but different depths. Because remember, of course, when we go in the field, you can size the length fairly reliably, but not the depth. And so if the crack is reported to you as 42 in the field, that will be this line in the middle. But what if it's actually deeper at 52 or if it's shallower? So this is something that needs to be done it's sort of a sensitivity analysis, and the calculator will allow you to do that, because if you know the toughness, you can't really predict what the failure pressure is. So you may have a range you have to work with, but also you may have a range of crack sizes you have to work with. So that gives you an idea what the prediction will be. So what are we testing? Well, of course, reinforced defect pipe samples with no defects and pipes with defects reinforced. Okay, sorry, with no repairs and with repairs. And here are the 2 pipe samples that we have: is 12-inch and 36-inch. Both of them are fairly old pipes, and we also will. We already had the material properties for them: fracture toughness and yield and all that. So we have 3 manufacturing companies providing. All of them will come in with carbon-based epoxy systems. Okay, Each of those manufacturers of the repair system will be responsible for bringing those tests into the program. They will install them themselves. We won't be testing different types of layers and all that. We have to reduce the variables, so they have to decide, the manufacturer have to decide in one arrangement, one type of carbon epoxy, and that's the one they're going to use for all the tests that we have. So we're going to subject the samples to about 72% SMI cyclic loading, and then we'll perform burst testing. We will then integrate the effects of, so we installed some of those repair systems with some pressure in the pipe, okay? All right, that's typically how it was done in the field anyway, so we wanted to test the effect of those. And some tests will be at a higher temperature than room temperature, like a 65 degrees Celsius. What are we not testing? Well, we're not testing multiple cracks, internal cracks, or circumferential cracks. There are single axial defects, okay? We're not gonna test the layers of the repair system, like I said, no other loaders, then just internal cyclic loading, no corrosion effect, and no effects on the microstructure. Here are the companies participating. So we have 9 pipeline operators. You see them here: Boardwalk, Enbridge, Eastman, Northern Natural, Plains, Southern Star, SoCal, TC, and my former employer, Williams. And the 3 repair companies are Allen Edwards, CSNRI, and Team. Okay. We appreciate the support by these 9 pipeline companies and the collaboration with the 3 repair manufacturers. And so this is being led by Chris and I. We're in some sort of imperfect troublemakers that were trying to learn something from testing pipes with defects and some special repairs. Here's the test matrix then. So we're going to test 12-inch, like I said. The 12-inch will have defects in the pipe body and the seam, okay? The 30-inch at this point, we don't have plans to add the seam weld defects on the 30-inch. So we have some fatigue tests and some initial baseline bursts, and the fatigue test will go beyond the 225,000 fatigue cycles, and we'll stop that and burst test them. Here, the ones that we're repairing. So it's the test matrix is quite extensive. We like the idea of having 3 tests at least with the same type of defect and repair. So the starting notch will be the source of that fatigue crack, as Atul mentioned. So we got the ADN notch, and then we'll pre-cycle, and the idea is to initiate a crack from the bottom of that defect. The challenge continues to be to stop the pre-cycling before that crack grows through wall or actually ruptures that sample. So we have a few ways to do it, generally with clip gauges and strain gauges across the notch itself allow us to have an idea how many cycles it takes for that crack to open up. As if the crack starts, then the mouth of that notch will be much opened in relationship to that crack at the front, and therefore that allows us to stop the pre-cycle. Okay, so here's a cross-section view of the starting notch for one of the samples. So that will be the generally the through-wall profile of it. It looks like a canoe shape, and then we go through the pre-cycle, and this particular sample shows up to failure. So here's how the fatigue growth, how that starting notch looks like a canoe shape. Well, actually, in this particular sample, the fatigue final size shows here in blue. So again, we have 2 pipelines, a 12-inch and a 30-inch, and here are the sizes of the starting notches that we decided are appropriate. So we got both of them have 3 inches long, and on the 12th inch will be a 30% dip and a little more for the 30-inch. Okay, here are the sample configurations. We have, again, samples that will have the starting notch right on the seam and the on the pipe body. All right, here's the project schedule. So we are up to this point. We're in January. Actually, February starts. Can you believe it? January is almost over. So we have machined. We already have the sample fabrication. We are starting to do the pre-cycles and start to initiate cracks from the bottom of those notches. All right. Any preguntas? I have time to answer a few of those questions. Ryan, back to you. How do we do it? Or Ashley? Any feedback? Can you hear me?
There you go. Go ahead, Ryan.
All right, Sergio, can you? No, I don't think it's on. Turn it. Oh, the button's off.
Testing, testing. I can hear you, Ryan.
All right, it's on now. All right, so I'm not sure exactly how this works. This will be our first kind of virtual question and answer part, but I guess live, are there any questions right now? Sergio, can you hear me?
I can.
We'll send you a text if you can't hear us.
No, I can hear you.
Oh.
Good.
Chris sent you a text.
He can hear. It's just that there's competing
Okay.
inputs.
Okay. Well, I think Ken had a question.
Yeah.
I'm going to give you the mic.
Yeah, really nice discussion.
Hey, turn around so I can see your face.
Turn around so you can see.
Okay.
Hey, how are you?
I'm not talking to him. Yeah, my question relates to in the composite, when you're applying the composite, are you doing it in the pressurized condition, in the unpressurized condition, or somewhere in between, to evaluate the effectiveness of the repair on the crack driving force?
Okay. Yeah. So the installation will be done both ways. Some will be installed with no pressure, and some will be installed with some pressure. I think we're looking, Chris, but not very high. I think around 30-40% smice. And we think that could affect the crack forces at the tip there. So in reality, what we're modeling is mostly the actual field application, because that's generally how the composite sleeves are applied in the field, with some type of line pressure. Operators don't drop the pressure to zero or close to zero when they apply composite sleeves. So that's the intent there, more than the crack behavior effects on it. So I can see one question submitted to me via text here. What do I see as a future for composite sleeve for repairing cracks and sort of planar defects? I think what I see it is that it does have a place in the toolbox for operators to use composite sleeve for repairing certain types of defects of certain sizes. And so this is one of the main objectives of this JIP, is to prove that. Like I said, I want to say it clearly and multiple times, is that composite sleeves are not applicable to all cracks, sizes, and types. Okay, there will be certain types, certain sizes of defects for which this will be appropriate, and that's what this JIP is aiming to demonstrate. Okay, so there is a question posted here on the screen by Fan. Fan is from Philip66 there in Houston. So in the cross section shown in the slide, is the crack in the pipe body or seam? Okay, so the image I showed there, Fan, is actually the SEC field in the pipe body. The one I used when I showed the crack growth progression, that's a SEC column in the pipe body. All right, looks like Fan continues on. He says, have you successfully fatigued grown cracks in low frequency bond line? Yes, we have, Fan. So it's a challenge to stop the pre-fatigue cyclic sequence before that crack grows to through wall. Generally, is what we'll expect. And so, yes, we have that, but we're, as Atul mentioned, we're looking at some of the techniques, acoustic or DCP, that is the recurrent potential drop techniques that are commonly used in laboratory settings to monitor crack growth. So that's what we're expecting to use and test in the future. Okay, Fan continues on. All right. So for A.O. Smith pipe, so that how do you define 35% deep crack? All right. So for those of you, A.O. Smith pipe is a type of seam that was left with some sort of raised square on the outside and raised square trim on the inside. So it's not a flash trim on the outside or inside of the pipe. And so the idea, we're not testing A.O. Smith pipe. I don't think the 30-inch. I don't think it's A.O. Smith pipe. Chris, correct? The seam type. Yeah. All right. Chris showing his thumbs up there. So what we will define it from the crack surface. Okay. So from the outside surface of the pipe. In this case, we don't have A.O. Smith, so will be the seam types that we're dealing with in this testing program fan. They're basically flash seam. Okay. All right. Any other? I don't see any other submitted questions. Remember, I can ask questions too. Can I ask questions,
Hey,
Chris?
Sergio, really good job, all the way from Houston. So I thought you might share a little bit about, I know we've talked with Steve and Chris with PHMSA, but kind of, if you're going to interject, kind of what are they looking for in a program like this, a good deliverable if you're putting yourself in their shoes.
Okay. All right. Yeah. So Chris and I had a meeting with Chris Hoydell and Steve Nanny. Those two individuals are with the sort of engineering part of the PHMSA, but also work with the enforcement. So they have that kind of unique perspective of not just being solely regulated, but also look at the engineering and sort of special permits and so on. And that's what this will lead to when operators will want to use composite sleeves to repair lack of fusions or cracks. So in the U.S., they will have to submit some type of special permit or notification to PHMSA, right? That they're using something that is not currently in the industry standards. So our meeting with them, they actually were excited, both of them, about this test program. And I think they were also, it was also nice that we involved them from the beginning of the test, not necessarily at the end when we have results to show. So I think it's important that we engage them from the beginning. So they appreciated that effort. And what they look for essentially is that we are demonstrating the performance of the repair systems just beyond, like I said, noted in the slide, beyond just reporting cycle to failures and so on. I think the idea is to look at the crack growth performance or reduction in growth by the repair system we're going to test. What I would expect from an operator in the US submitting a request to PHMSA is that they will look at the data that we're going to test for sure, but also look at the unique pipe conditions that they have for which they want to request a special permits. In other words, so what's the fatigue conditions? Where is it located? Are there landslides nearby? So they're looking at external factors that could exacerbate the performance of the repair systems under the conditions for which were tested. Because remember, any testing that you do, whether full scale or subscale, you're trying to replicate what the actual pipe experiences in the field. So we're not accounting for all the possible variables. We're just looking at internal loading, cyclic loading in this case. So what I would expect is that they would include, what external factors are in the location of the repair, the type of defect, the location, and of course you have to show some engineering analysis. You did that defect type and size is actually in a subcritical regime or region that you expect, to be sufficiently safe. What we're going to do in the cyclic loading, as you notice, is delta P 72%. That's very aggressive, and really the reason is so we have to test a lot of samples, and we don't want to spend 2 or 3 years testing all those in the program. So we have to obviously simulate more aggressive conditions to have a more reasonable test time frame. And so we have to convert the cyclic loading of the sample, correlate that to what the pipe sees in terms of cyclic loading. And we have ways to do that, like the cyclic index. So that will be another connection that the regulator would like to see, is how the cycles to failure, compared to what the actual pipe life based on the actual cyclic loading that the pipe sees. Hopefully that helps, Chris, and the rest of you. All right, I have a few more minutes. Another question or comment? Chris, I think the presentation will be made available, correct? When I say that, I couldn't see your thumbs up because I was presenting. Looks like Ryan is nodding, so he's good. All right, I have a question for you, Ryan. Can you hear me? Ashley asked Ryan what happened to his finger, with his pinky finger.
Can you hear me?
I
Yeah,
can
well,
now.
talking about fracture, I decided to fracture my hand before this event. No, about 3 weeks ago, I had a little accident.
Have you done
on
a
walkway.
fracture analysis?
Great.
Have you done a bone fracture analysis?
Not very exciting,
Is it-
honestly.
Ryan, is that a carbon
Yeah,
fiber
it's
composite?
the
Is that what you have? What is it?
What's
All
that?
right. Is it a carbon fiber wrap on your hand? What material is it?
CSNRI put it on one day for me.
Oh, okay. All right.
That's right.
We don't know how we're
All right. Thank you, everyone. Thank you, Chris, for the
All right.
opportunity. Good job, Ashley. And now for Rhett and the rest of the presenters remotely, I think you have an idea how this thing is going to work.
All right, Sergio. Can you hear me now? All right. Yeah, thank you, Sergio. Really good talk. I just want to highlight real fast before we take a 30-minute break is that, if you can see, especially people who are virtual, this testing Sergio mentioned, it started earlier this month, and we've tested about 10 of these pipes, and the big green boxes you can see in the back, that's where all this testing is occurring. So if people who aren't involved, if you have some more questions, feel free to reach out to Sergio, Chris, or myself, and we can give you some more information. And if you want to get involved in this project as we're kicking it off, please let us know. So yeah, so right now it's a 30-minute break. People at home go and do whatever. Yeah, have your peanut butter sandwich, and we're gonna just kind of wander around here. So join us back at 10:30 sharp. Central Time. All right, thank you guys. Can the virtual folks see us? All right. Well, thank you very much. So our next presenter is Ken Bagnoli. He's been with ExxonMobil for about 30 years. He has degrees from Stevens Institute of Technology and a master's from Columbia in material science. He's been more on the refining side at Exxon for 30 years. But probably about 8 years ago, he became an honorary pipeliner. And,
Never look back.
yeah, never look back. That's right. So what he's going to be presenting, and I kind of highlighted during my talk, but he's going to share some results of a study that occurred over the past 4 years or so, where we characterized the fracture toughness of vintage pipelines. And he's going to start sharing some of that data now.
Okay, and do we just hold this one?
Yeah, or clip to yourself.
Yeah, that'll probably be easier. All right, is that audio
We're
good
good.
to go? And this is back, I think. Okay, all right. Okay, well, thank you, Ryan. Yeah, thanks for ADB to organize this conference. There's a lot of good topics, and they're very timely. And I'll mention why, I think, as I walk through my talk. I'm going to say at the outset that, while the title of the talk is, more around database, of testing, and I will show a lot of data, a lot of generated by my friend here, Edgar Zapata at Anderson Associates. But more importantly, I wanted to share what ExxonMobil's view is philosophically around dealing with seam integrity, and specifically focusing in this particular talk on fracture toughness. You'll also see a few slides that are similar to Ryan's, and that's because Ryan and I were partners in a lot of this work for the last, quite a number of years. So, okay, so I'll give a little bit of introduction, but a lot of the topics and the scene setting has already been, discussed. I'll talk a bit about mechanisms of crack growth. We didn't stop at just sort of running lots of tests. We wanted to know why we were getting the fracture toughness values that we were getting. Were we getting brittle behavior? Were we not getting brittle behavior? And I'll tell you right now, and in the testing we ran, I'll show you about 450 fracture toughness tests in the stock. About 70% of them did not fail in cleavage, which is a little counterintuitive relative to the low Sharpie values that people, may have gotten, and that would have implied. Then I'll go into more around the results of an extensive amount of compact tension tests from a wide spectrum of different pipelines. And again, Edgar was very helpful in conducting that test work. The latter topics are, I want to introduce them here. They are rather complex, and I will try to describe it in a way that shows the meaningfulness of why we've done it. But I'll say at the outset that compact tension specimens, or if you look at the hierarchy of testing, you have Sharpie tests, which are very easy to conduct, but are only roughly correlated to fracture toughness for a variety of reasons, right? But they're easy and they're cheap to run, right? But they're not a great indicator of actual fracture toughness. Then you have compact tension specimens, which have become much more cost-effective to run and are a direct measure of fracture toughness, but they don't replicate really the loading of an axial crack in a cylinder. And then the most precise measurement is this last topic I'll discuss, which is a testing method that measures and loads a specimen in an identical manner, so you really get the best representation of fracture toughness. Okay. So Ryan's already discussed, kind of the scene set around the vintage pipeline. I think we all know that, both on the gas side and on the liquid side. You know, we have a lot of low frequency high frequency pipe pre-1970, which, you know, has high sulfur steels and fabrication related, manufacturing related features. One point I did want to make though is that, you know, we've tested the weld center line, base material, and heat affected zone. And while a lot of effort is given to the weld center line, when you look at the types of defects like hook cracks and others, a vast majority of them are growing off, you know, off the bond line. And so it is important to understand the properties, you know, in the surrounding weld region, not just the bond line. Okay, so this is a little bit of our sort of philosophical statement about ExxonMobil's approach to fracture toughness. So, I mean, our going in position was, if you take isolated data from digs, that's very useful, right? But you're extrapolating those results to, you know, an entire pipeline that may involve different manufacturers, and so forth, and the properties may vary, right? So how do you address that? Our approach really was to say, to address it in a holistic manner. Let's look at all the types of pipes, pre-1970 type pipe that's out there, many manufacturers, many, you know, high frequency, low frequency, and characterize this whole class of materials, to develop a statistical database so that digs are now used to reinforce that. But for assessments of seam integrity, you could rely on an underlying database that encompasses the entirety of those classes of materials. I mentioned Sharpie tests.
Change the microphone.
Oh, I'm sorry.
Sorry. It's just hitting your, there we go.
Oh, okay. I don't have to start over again, do I? I can. Okay. I'm good? All right, great. Yeah, I mentioned Sharpie tests and the limitations of Sharpie. I don't want to, look, I know we and most of the companies represented here, or maybe on the simulcast, often use Sharpie tests, right? And they do provide good, useful information. There's no doubt about that. But a Sharpie test is not a fracture toughness test. And fracture toughness is what you use to make the kind of calculations that Ryan and Sergio and others had discussed previously. And that means that you need to test and correlate that. And there's lots of correlations that can be used. You know, it's a dynamic test, right? Pipelines are not loaded in a dynamic fashion. They're loaded in a slow loading condition, the way fracture toughness tests are loaded. They're loaded slowly. They also, because it's a notch and not a crack, they sample a much larger amount of material. You don't have the ability to locate, like that Sergio showed that sharp crack, you know, from that notch. You don't have the ability to say, well, I want to put my little crack right on the bond line, or right in the heat affected zone, or right in the base material, right? So you're not really sure what you're testing. Okay, and so for those reasons, and of course, you know, lastly, although this is not an enormous issue, but you know, we're always testing subsize Sharpie tests now. They can be obviously converted to full size Sharpie, but that's again yet another correlation involved. Okay, so we focused on developing a database using fracture toughness specimens. Which initially involved these compact tension specimens, and then we moved on to a specialized specimen that I'll discuss. So, overview of the database. At this point, you know, we have well over 400 fracture toughness tests that we've analyzed to this point. We continue to take more and add to that database. About 360 odd ones are compact tension. about 116 are these single edge notch tension specimens. Those are the ones where we're loading them in an identical fashion to an axial flaw in a pipe. And I'll show you some pictures there that make that more clear. We've got 14 different pipelines, multiple pipe mills, multiple vintages, low frequency, high frequency welds, bond line, heat affected zone, and base material. We looked at heat treated, non-heat treated. So we tried to really span the gamut. We conducted the testing mostly in the room temperature range. It's always a bit of a approximation, but for buried pipelines, we felt like that was at least representative. And also, when you're doing lots of tests, you want to try to compare them on a equal basis. And if we did testing at lots of different temperatures, then you can confound things. Although we did explore temperature ranges as part of this overall study. So I said at the beginning that one of our objectives here was not just to generate tons of data, right? We really wanted to explain, all right, why are we getting values that we get, right? I mean, if we measure a certain value, does that relate to the actual pipe manufacturer or the quality of the steel, that sort of thing? So we did quite a bit of characterization work to do that. Now, you'll, I think, all recognize, tell me if I step out of view here of the, am I good? Yeah. Most of you will recognize, a hook crack that I've shown there. In this particular case, it was the nicest one I could find. You can see that a hook crack is then the initial flaw. It grew due to fatigue, and it tend to follow these, kind of bands of inclusions that Ryan discussed at the outset, where you're pushing the pipe together and you're creating these hook-shaped manganese sulfide inclusions. And then when that flaw reached about 50% of the wall thickness, it failed in cleavage in this particular case. And then at the end, that's called a shear lip. So at the very end of the failure, you'll always see just a little shear lip. Okay. So what I'm about to show here is a 3D X-ray microtomography. This is a kind of state-of-the-art technology that we have the luxury to have. But what it does do, it's basically a CAT scan, okay, that shows you in 3 dimensions what the crack looks like and how it's interacting with these manganese sulfide inclusions. So if you can run this video. Oh, can I do it from here? It's on the, yeah. Okay, so what you're seeing here is a sample from a pipe with a crack, a real crack. And what we're going to do is now, like a CAT scan, cut through this specimen. So you can see we're slicing through the specimen at this point, and you can see the different shape. Okay, and in a minute, what you will do is we will back out what the actual crack looks like. So this is the crack in 3 dimensions. It's following an inclusion field, and you can see on the front side of the crack another inclusion, okay? And that crack will then jump, that ligament will fail, okay? That's an important, and I'll, you can go to the next one, Ryan. That's an important thing to understand, because even though we have this general perception that ERW pre-1970 pipe is, poor toughness, okay, and I'm not arguing it's a high toughness material, right? But in this particular case, because you have because the way cracks grow and progress in ERW pipelines, they interact with all those all the inclusions. And in fact, the inclusions tend to grow together, as opposed to like when you have a cleavage, a brittle fracture, you have a small defect, it triggers a failure, which is a statistical event, and it fractures and it runs. But the way cracks tend to grow in ERW pipelines is they tend to grow through these inclusion fields. On the right here, I know you probably can't see that real well, but what I'm showing is these large manganese sulfide inclusions. And then this picture, nothing new here. I mean, the Patel folks did a lot of work. They coined the term, I think, woody fracture. And so that woody fracture really is the tortuous stepping of the crack as it hits those different inclusions. If you remember that movie, you saw that flaw, and then you saw another big inclusion in front of it, right? And so if you do some finite element work, you can sort of look at, and we did this modeling, to try to look at how these sort of non-planar layers of inclusions would have the greater tendency to join before it would fracture. Okay. So next one here. Here again, this is a little bit more of the same. This was a test where we performed a fracture test. The fracture surface was covered with manganese sulfide, demonstrating that it's following that path. And this is, again, a 3D image showing this flaw here. And again, it's showing a flaw with another flaw that it's about to connect with. And that's exactly what you're seeing here in 3 dimensions. So I think the takeaway here, though, is, all this sort of high-tech business aside, I mean, the bottom line is that this image here really shows what we believe, after quite a bit of effort, how these ERW pipes fail. The implication of that is, why do they fail and give the properties, the fracture toughness properties that they give, right? And that's what I'm about to get into. Okay, so just a quick image here, showing a typical compact tension specimen, and Edgar Zapata from Anderson Associates has done really a vast majority of our compact tension, especially he may probably discuss this in more detail. I'm not sure, I haven't seen your talk, but in any event, he was meticulous at etching specimens, placing a scribe, placing as best as possible. I mean, this is not perfect. These bond lines are not always straight. There are practicalities and compromises you have to make. But we would make an attempt to test the bond line, okay? Heat affected zone, which was typically 1 millimeter to 1.5 millimeters off the bond line, and then in the base material, okay? So that was our compact tension specimens. This is a busy slide, but it's an important one, okay? I hope I'm going to be able to convey, I'll do my best, but it is an important one. And it gets to this discrepancy or difference between Sharpie and running fracture toughness tests. And I will say, by the way, people tend to run Sharpie tests because they're cheap, right? Compact tension specimens like the ones I showed are not that much more difficult or expensive to run, and they yield a tremendous amount more information. So I will make a plug for, Edgar and other labs that do that kind of testing. You generate a lot better information at a little cost. So if you're, and the folks in the room probably have difficulty, but the people online probably have a better image. But what I'm showing here on the left are a bunch of Sharpie data, okay? Now, the open diamonds open squares and open triangles, okay, are the Sharpie impact values we took from a particular low-frequency ERW bond seam, okay? And so you can see the foot-pounds were in the range of, on the bond line, about, I don't know, 2 or 3. We were up around the 6 range, or so in the heat-affected zone, and in the base material, we were up around 10. Now, if you convert, like you have to, those Sharpie values into a fracture toughness value, okay, and this just happens to be one of about a dozen different correlations. This is a common one. It's in API 579, for example. These are the toughness values you would get. So if I just look at the bond line, okay, I tested the bond line and I'm getting values in the couple of foot-pounds range. If I use this sort of empirical correlation, that's implying a fracture toughness of about 10, okay? All right, so keep that in mind. Now, I take the very, very same seam, okay, identical seam, but now I run fracture toughness tests. In these cases, a little bit different geometry than the compact tension. These were, but a bend type specimen, okay, from the same locations. And look at the values you're getting here on the weld center line. Here we were predicting from Sharpie values of 10, 15, which is extremely low, by the way. I mean, that's that would be lower than that most people would ever assume for a fracture toughness in any other environment outside the pipeline industry. But here, running a proper fracture toughness test, we're getting values of about 40, okay? With the heat affected zone, we're getting values of about 60, okay? And in the base material, values in the range of 100, all right? So you can see there's a significant difference. It does go back, again, to the nature of the way these tests are run. You're whacking a Sharpie bar, in a dynamic test. It's correlated in size and the fact that it's not a true measure of toughness. And I'll make a third point here, which is we ran a few additional tests with this so-called SENT, which I'm going to speak more about. That specimen is basically loading, it's a fracture toughness specimen, and I'll show you pictures of it, that's loaded in tension. Now, if you think of an axial flaw in a pipe, right, the opening stress is the hoop stress, right? That's a pure tension loaded, essentially a pure tension loaded specimen. So these type of specimens are load the crack in tension. So they load them the same way. And if you notice here, these were for heat affected zone. It provided about another 15 or 20% higher value. It's these X's, right, versus these green triangles at these two different temperatures, and you can see a much higher toughness. So this, we would argue, is the quote unquote most true toughness of the material. Okay, I'll move quickly. Okay, I won't belabor this, but this is just many of you may not be familiar with J-integral testing, but when tests don't fail in cleavage, you generate a tearing curve. Okay, and from this kind of tearing curve, you can infer a fracture toughness. And for 2/3 or 3/4 of it, we had to do that. Whoops. Ryan showed this before. Again, it just shows that compact tension is going to give you a very conservative value of toughness. These tension-loaded specimens give you a much better, closer to an axial flaw in a pipe. So we started taking specimens. These are the kinds we were taking. We designed a new tension-loaded specimen, and the features of that specimen are not only that it's loaded in tension, it also is oriented in the through thickness direction. And that's the direction that cracks actually grow. Cracks are not growing, predominantly in the length direction, although due to fatigue, they grow in both, right? But they're predominantly growing in the depth direction because the stress intensity is higher there. So these tests are probably the most representative. This slide, I'm not going to spend any time on except to tell you that we did an extensive amount of finite element work to make sure that that the toughness versus this parameter Q, which basically is basically telling you how close a match it is to to the pipe, right? So these two dark lines are what the toughness would be for a pipe. These are the different specimens, and we were able to basically design a specimen to what they call constraint match or load match, a pipe. Okay, this is just a quick, we can do this just quickly. I did want to show you actually how we're fabricating these things, because that's a big part of it, right? All right, so, but we plan to share all the details of the drawings and et cetera. But basically, we machine them out of the pipe wall in full thickness. We call that a chiclet. It's a very, very small little bar. We weld that to two shoulders. Okay. This happens to be with the EB welded design. There's probably different ways it could be done, but and then we do the final machining into the SENT specimen. We machine an integral knife edge. Okay, that happens to be the bond line, and then we instrument the. Yep, you can see we etch it, and we, just as Edgar does, and then we we use both unloading compliance as well as DC potential drop to make the fracture measurement. Okay, that's all I want to cover on that. So that's our specimen we call CSR SENT specimen. One other thing I wanted to tie this back to what I said earlier around tying the fracture measurement, the toughness measurement, to the physical cracking and what's happening with with the way a crack grows in the steel. Now, if you this happens to be an image that's basically showing like a bond line, and you can see the bands of manganese sulfide, right? So the expectation was, and in one of the early slides I showed, was that the cracks would grow sort of along those weakened bands, right? So we ran some of these specialized specimens, and we did very high resolution, what's called digital image correlation, okay? It basically shows you the strain field. This is the strain field, and this is the strain rate field. The important takeaway here, and the most important takeaway here, is that the strain fields are basically following these weakened bands of manganese sulfide. So the bottom line here was we designed a specimen that matches the loading condition, identically or nearly identically, and then confirmed that when you run the test, the way the crack propagates is the same way it propagates in a pipe. Okay. Okay, so back to some data here. This is a slide showing data from just some both our SENT and our compact tension. This is for the weld center line. Okay, and what you can see is that we're getting mean values. The distribution is wide. We're getting mean values in the area of about 60 or a little bit higher for compact tension. But when you actually test it in a manner that is a true indication of fracture toughness, it's over 100. Okay, it's over 100, and I did show the other histogram, didn't I? I skipped over it. Okay. All right. Yeah. One of the most important slides here I skipped over. Sorry, guys. This is a database of compact tension specimens comparing the bond line, heat affected zone, and the base material. Okay. So we've characterized those statistically. These data can be used directly both in a deterministic or probabilistic analysis. Okay. So for instance, if you found flaws in the in and around the bond line, deterministically, you can choose whatever confidence interval you're comfortable with. We are starting to go much more into the probabilistics area, so that requires a full, distribution of values. I would say that from our view, if you look at the way all those cracks grow, hook cracks and whatnot, they're all sort of meandering generally, except for the lack of fusion flaws, which a lot of them are penetrators, anyway. But a lot of them are meandering around those hook cracks and are growing kind of into the heat affected zone. So the combination of this heat affected zone and bond line distributions is probably the most representative way of determining fracture toughness, your best estimate, okay? But you can do a lot with the, given, that we understand the statistics of it, you can make use of that. So I will jump ahead here to my conclusions, okay? So the bottom line is, we really had quite an extensive program to characterize pre-1970 pipe. The objective being, again, to kind of reiterate it, philosophically, not just taking data from a dig or a couple of digs and extrapolating that too broadly to an entire pipeline, but we wanted to characterize the whole class of materials, which is, I will tell you, is done in all other sort of avenues or all other industries. So if you were in the refining industry, where I spend most of my time, or at least I used to, we'll go to API 579 and we'll look up a certain steel, and there's a curve there, and we'll look up a toughness because that toughness has been characterized as a class of materials. And I would argue, and we at ExxonMobil would argue, that that's a much more effective way of choosing toughness. A number of other things I've mentioned here in terms of, the broad sample. We feel like we've done enough at this point, enough vintages and manufacturers and so forth. We have, and we'll be sharing in the future more specific details around these specimens. Like, obviously I showed you a little movie, and I don't think Edgar's that's not gonna be enough, right? But we will publish specific drawings, machining, and welding guidance for how to prepare those specimens if someone wanted to do those. We intend to publish and continue to share more details of the statistics. Although I've shared here with you today the statistics around our database. So with that, thank you, and I'll take any questions anybody has.
So we're kind of running behind schedule a little bit, so I'll just ask kind of one quick question to you. You can describe a little bit philosophically how you plan to share this data with the industry as a whole, and you plan to publish in various standards and whatnot.
Well, right now API 1176 is being updated. So our intention is to donate this fracture toughness database into that standard so it can be used by the industry. There are a variety of venues. We'll be sharing this kind of information at the next PRCI Rex meeting. We'll probably publish more details around the machining and more practical aspects, at IPC and those, particularly that kind of venue. So those are the kind of ways we plan to share that. I mean, I would say that we also have a JIP ongoing, which Jason Skow may talk about later. We donated all of our data to that JIP, which is a development of a tool to do probabilistic analysis, a tool that is not meant for data scientist at NASA, right? It's designed for pipeline integrity engineers to be able to do a probabilistic or deterministic analysis in a straightforward way to help in decision making. So they have access to all that data, and so I'll make a little plug for that JIP if people are interested in that. So, all right, okay, thank you.
Yeah, thank you, Ken, very much. Here at ADV, we use Edgar quite a bit. As Ken mentioned, when you need fracture testing, there's, not all labs can perform fracture tests, but Edgar is very accomplished in that area and very timely for that regard. So with that, I think Edgar's going to share some more details about some of his fracture toughness testing capabilities.
Is that good? Is that good? All right. Well, good morning. Thanks for inviting me. And just a little bit about myself. My name is Edgar Zapata. It's been mentioned. I'm president of Anderson Associates. And I started this whole trip about 35 years ago. I took this engineering design class at Texas A&M. And one of the chapters dealt with fracture mechanics. And I thought that was the coolest thing, be able to predict a critical flaw size. And the professor in that course was Richard Alexander, Chris's father. So it's kind of a small incestuous culture here. But anyway, just talk a little bit about fracture mechanics. I went on to pursue that, ended up taking a job with Anderson Associates about over 30 years ago. Now I run it. So the basic question is you have a pipeline, and stress analysis is well defined, as one of our former presidents was fond of saying, the science is settled. Well, when it comes to flaws, maybe not so much, right? This fracture mechanics is kind of a growing and in progress science. I mean, we're learning more as time goes on. I mean, we saw a tool show us that, we're not exactly predicting burst pressures because of constraint problems and testing. So it's just, it's in flux, and we're learning more as time goes by. A couple of things as far as sample orientation, which I think Ken alluded to. We, back in Sharpie testing days, you would ask for a longitudinal or a transverse, right? Sharpie test. And longitudinal would mean, the bar is running long ways and the fracture is propagating circumferentially. And a transverse would be, it's oriented circumferentially and the fracture would run longitudinally. But that doesn't completely define the crack plane, right? There's another possible way of taking a longitudinal specimen with the crack running radially, right? Or there's another way of taking a transverse specimen with the crack also running radially. So in fracture mechanics, we have a nomenclature that kind of defines the crack plane. The first letter will tell you the normal to the crack plane. So if you have a CL specimen, which would normally be a transverse Sharpie specimen, the crack plane is normal to the circumferential direction and running longitudinally, right? And if you have an LC specimen, it's perpendicular to the longitudinal direction, running circumferentially. And don't get those two mixed up, right? Because if you ask me to test in the LC direction, but you really meant CL, you're going to get very different answers. For pipeline under pressure and testing seam weld, most of the time we're doing CL direction testing. For girth weld testing, you would do LC, or if it's loaded and bending, if your pipe's loaded and bending, or some sort of longitudinal stresses, you would want to do LC. Ideally, like Ken said, the direction of propagation is LR, or sorry, it is a CR, it's a radially propagating crack. But most of the line pipe that we have, the wall thickness is very small. Now, with that new specimen, which I'm curious to see how that'll come into use, that's probably a better orientation. But for now, what we're doing is we're testing CL direction specimens. And this is just a picture of what it would look like. This is the normal orientation. And here we go with the Sharpie bar, similarly oriented. You would say that that's a transverse bar, but it would be better to call it a CL specimen. Sometimes we come into problems because of the curvature of the curvature and wall thickness don't allow us to get a full-size bar. So we end up with either sub-size bars, or we also have modified bars, and that's the result of that. Sometimes we need to flatten the bar, and I know that kind of is a little bit controversial because you are plastically deforming it. I would argue that, especially if you're doing seam weld bond line testing, the higher hardness is in the bond line heat affected zone, and most of your deformation on flattening is going to be on the arms and not in the area that you're going to be testing. So, and then on top of that, we're going to be machining off the ID and the OD, so those are the most highly strained areas. There is some sacrifice, and I understand that you are introducing a variable, but sometimes that's what's needed. And I mean, if you send a 4.5-inch pipe with a 1/4-inch wall, it will have to be flattened to get the test. And I'm just based on data that we've seen, testing seam welds, you do get variation, and it does show when you have problems, because you do find low values and you find where you have your problems. So it is a valid test. As was shown in Ken's slide, hitting that seam weld is a little challenging, and it does require, etching it both before you machine it and then after you notch it to verify that you are testing what you think you're testing. Let me talk a little bit about Sharpie testing. Back when I started this and I'd go to these ASTM committee meetings, the comment was, oh, Sharpie testing, that's gonna be gone. In 20 years, that'll be gone. Well, here I am 30 years later, we're breaking more Sharpie bars than I've ever broken before. So and the reason is it's cheap, it's easy, fast, and it does measure something. And it does measure relative quality. And we know that, 60 foot-pounds is tough and 5 foot-pounds is not tough. And so we do know that. But as Ken said, it's measuring something different, right? It is a dynamic test versus your structures that are statically loaded. And, there are different things going on. Just talk a little bit about the Sharpie test itself. This is the fracture surface on the Sharpie bar. There are a couple of things you can measure besides the impact energy, which is the energy absorbed during fracture. You can measure the amount of lateral expansion, and again, that's a relative measure of toughness. You can kind of conceptually visualize that the more the back of the bar mushrooms out, the tougher it is. And I see that in stainless steels. They like to judge their toughness with Mills lateral expansion. Another measure of toughness is the percent shear. Now I've shown in here in red, that's actually circling the brittle fracture area. So everything outside of it is, what we would call shear. Now it's not actually shear because the notch at the bottom, and then from that notch, it's tearing in the same plane as the notch, and then it fractures brittly, but then on the side, it's shearing at 45. So there's a lot going on in terms of fracture, and you're just reporting, an energy measure from. Another variation is size. What I showed in the previous slide was a full-size bar, but a lot of times in pipelines we have thinner materials, so we need to take half size or even less bar, and then there's correlation problems with that. Again, just showing trying to hit that seam well bond line. You have to etch it and show that you're hitting that bond line. So one of the things that you can develop with Sharpie testing is a transition curve. For ferritic steels, there is a change in toughness with temperature, and you can plot that, and that becomes maybe a little bit more useful than just simply the single energy value. So just to recap, the energy you're measuring doesn't really distinguish between initiation, propagation. It doesn't distinguish. I mean, you can even encompass for tougher materials ductile deformation of the bar, the arms of the bar, so you don't know exactly what you're measuring. The energy that you're measuring is not directly applicable to a structure. You can't take that number, an energy number, and say, well, I can calculate anything. You basically have to rely on empirical conversions. But if you use a transition curve, there might be some hope for trying to use those values. So fracture mechanics is basically trying to deals with, and we've seen that slide, we're relating the material toughness, the applied stress intensity, and the flaw size, right? This is basically a linear elastic model, and if we were to measure the fracture toughness, we would measure it something like this. We would load up our specimen, and it would fracture. We would need a behavior like this to measure what's called a K1C fracture test. But most of our materials behave like this, so they're not going to give us a valid K1C linear elastic fracture toughness value. So there are other fracture toughness testing methods. One of them is a CTOD, which stands for crack tip opening displacement. And basically what you need in fracture mechanics is a infinitely sharp crack, right? And the only way you can really get that is, you can't really machine that. You can't, as Atul mentioned, you can't use a notch. You need a crack, and a fatigue crack is basically the sharpest thing that we can produce. So we machine a bar, we machine a notch, and then at the tip of the notch, by cyclically loading the specimen, you grow a sharp fatigue crack. And that's called fatigue pre-cracking because you do that before the test. The test actually is a slow time test. You slowly load the specimen, measure the load, and measure the opening. Now you can't really measure the opening at the tip of the crack, so you measure it, removed from there. And originally the calculation was just by geometry. You estimate the tip, and you get that opening at max load would be the CTOD. It's conceptually a very which would be your valid K1C fracture toughness. Now, as science develops, we're finding out that that's not exactly true because there's statistical things going on. But that present the problem with doing a simple K1C test versus a CTOD test. Another way of characterizing the fracture toughness and maybe more ductile materials is using a J integral test, which is based on a line integral around the crack tip, and it's a little bit higher level math, and is not as affected by the plasticity, so you can do it with plastically deformed material ahead of the crack. And basically what it entails is loading your specimen, And we like to use compact tension specimens for that particular test. Although you can use 3-point bend, single edge notch bend specimens. And basically what you entail is loading your specimen and doing these multiple unloads. And hopefully you can see it from the graph, but you can see that the slope at the last unload is shallower than the slope at the beginning. And the reason for that is because as your bar tears, you're losing compliance. So that's why this is called an unloading compliance. You're measuring the amount of tearing as you're loading the specimen. So each one of those load, unload points, you can measure the area under the curve, you can measure the amount of tearing, and you produce a crack growth resistance curve, a J delta A curve, and that'll characterize how the ductile material tears. And there's an idea that we have, if it tears a really small certain amount, we call that the initiation of tearing, and we call that the J1C. And we can use that as our fracture toughness number. Now, going back to maybe more brittle materials, or materials that fail unstably, we know that all materials basically follow the same curve, right? It's just that the position of that curve is different. So, there is a way to characterize your material toughness with respect to temperature, and that is using a master curve approach, and that's the testing for that's detailed in ASTM E 1921. And basically what it entails is developing a temperature that defines that curve. You can estimate that temperature from the Sharpie transition curve also. So if you have the Sharpie transition temperature at 28 joules and then you subtract 18 degrees, you'll estimate the 100 MPa square meter temperature. And since you know that temperature, you know the entire curve, and you can say, well, at some other temperature, my toughness can be estimated. And this is probably a better, or that's kind of the way things are heading as far as defining fracture toughness. And just to give you an idea, there's some testing we did where we estimated the initial temperature, tested 6 specimens, used those 6 specimens to estimate, make a second estimate of the temperature, tested 4 more, and then came up with the temperature that defined the 100 MPa square meter temperature, and that pretty much defines the fracture toughness curve. So just to recap, fracture toughness can use along with stress analysis. I think we've seen that many times in slides, along with special limits to determine a relative safety of the structure. You can also use it to determine the conditions that developed a fracture. And there are different methods out there to help you develop these parameters. And that's what I have.
All right, thank you, Edgar. So I think we still have a little time, and since Ken went a little longer, I don't know if you guys if you have questions for either Edgar or Ken, that would be a great time to ask those right now.
There was a question for Ken on the live stream. Let me pull it up. It was from Fan again, so.
Good job, Fan.
And I don't know how to read this, so you'll have to translate it. But it's a non-body, HAC and bond lines shown near the end of the presentation. Are those from CT or SENT?
Yeah. Hey, Fan, how you doing? Yeah, that's a good question. Those were all compact tension specimens. So the second set of distributions that I showed were comparing just the weld center line of the compact tension, that portion of the database, with the SENT tests. All the SENT tests we did were on the weld setter line.
I've got one right here.
All right, Chris has a question.
So Edgar, you and I have been doing this a long time. So if you look into the future, 15 to 20 years from now, how do you see, the material testing that you're doing changing? There's some newer technologies coming up that allow you to evaluate materials better. So I'm sure you maybe have some thoughts on that, or maybe you don't.
I don't know. It seems like with all the databases, maybe I'm out of a job. But really, I think material testing is always going to be there. There's always the question of yes, we have our theories, we have our models, but verification, right? Trust but verify. Specifically, we're starting to do, I guess what's called strain limit damage testing. I haven't really seen a whole lot of that in pipeline testing, but it has to do with what happens after on a tensile specimen, what happens after max load, and where does microvoid coalescence start, and trying to define that region.
Some of the strain-based design that would be important.
Yeah, definitely. So that's. It's hard to see into the future.
Any more questions?
There is a question from Sergio, actually. He's still hanging out with me.
All right.
And it is for Ken. And it says, would you speak more about the fracture behavior for the ERW bond line CT tests? You mentioned cleavage fracture was not predominant. Is that right?
Right, yeah. One of the things that we found that was somewhat unexpected, because the going in perception is that that these materials, the old low frequency W pipe, are very low toughness, and I wouldn't characterize them as high toughness materials. But as we tried to show with some of the microstructural work, and this is why we did that work, was we were finding that the vast majority, and Edgar alluded to this as well, were failing not in brittle cleavage. They were actually exhibiting stable tearing. And that was a little unexpected, particularly on the bond line. And so we wanted to understand that more. And we believe, I think we have a fair amount of evidence that shows that the basis is, because of the inclusions, it's kind of, the crack growth is mediated by the presence of those manganese sulfide inclusions that then you get essentially plastic collapse between those ligaments. And that's helpful in mediating cleavage fracture. That's not to say that you can't, but in the vast majority of cases, since pipelines are also thin wall structures, axial flaws or even circumferential flaws are under very, very low constraint. Okay, so when you combine the microstructural effects and you combine the fact that the crack is under low constraint, and when I say constraint, what I mean there is that if you test the specimen in tension versus bending, the bending specimen is going to give you a lower value, right? But an axial flaw in a pipe is loaded in virtually in pure tension by the hook stress. So if you load a specimen in the same way that it's loaded, a crack is loaded in a pipe, you get a better measure of toughness, and in fact a higher measure of toughness. And that all deals with this concept of constraint theory, which I alluded to in the design of the specimens. Probably would be a much more lengthy discussion. So.
All right, any more questions? All right. I think we are ready to break for lunch here. So for the next hour, we're going to have some lunch, and we'll come back at 12:30. Rhett Dotson, he'll be the next presenter at 12:30 from ROSEN, so we'll get a little more on the inspection side after lunch. All right, thank you, guys. before lunch, I'm going to be talking more about ROSEN's inspection capabilities. Actually, okay. Rhett, can you hear us?
I can. Can you hear me? So that's a yes, and you're good for me to go? Yeah, all right. I understand. Thumbs up. All right. Well, good afternoon, everyone. It's a pleasure to be with you guys. Ryan, Chris, thanks for having me. In the interest of full disclosure and confession, I found out 10 minutes ago that my presentation started in 10 minutes, and I found out 10 minutes ago that it was 30 minutes, not an hour. So 10 minutes ago, I didn't even have a shirt on. So and I had to chop the slides down from 75 to 55 to get through in 30 minutes. So hey, we're along for a great ride. And I was told though that Ryan said there's only a lab tour after this. He basically said I have an infinite amount of time, which I intend to take full advantage of, Ryan. So let's roll. And I can't hear any of you guys, which is really unfortunate. So that means all of my jokes, they either get laughed at or they get snickered, and I can't tell which one. But we're going to have plenty of them in this presentation. So I'm here today. They asked me to talk about cracks, inspection technology with ROSEN. I hope to give you a little more than that, not just simply what's going on with cracks, and so or at least inspection technology. And a lot of what you're going to hear me talk about is that it's more than just the technology. I think people want to think about tools. They want to think about running EMAT, but there's more that goes into running EMAT than just the technology itself. Okay. And so before we get started, it's been a long time since I presented with Chris Alexander, and I knew he would appreciate a despair, especially since we have a whole bunch of consultants talking to a whole bunch of operators. And the truth is, we're here to help you guys, but hopefully it's more than solving the problem, not prolonging it, right? We're here to help you make sure that you get the best out of your inspection, whether that's understanding the data you've got, dealing with the material properties, or really understanding which features to go after. So let's begin. What's the problem? What are we after? And I'm not going to talk about this for too long because you guys have probably already had several other presentations on this today. But when we talk about things that we're interested in, particularly in the sphere of gas pipelines, we start with pipe bodily anomalies, whether we're talking about, and that's predominantly SCC, right? And it comes in the near neutral and high pH flavors. But there are other things that we're interested in, such as third-party damage that comes in the form of cracks and gouges, or whether or not we're talking about laminations or even axial fatigue cracks. Then we also move into seam defects, of which we're predominantly concerned with selective seam weld corrosion, hook cracks, and the like. When we talk about a crack detection technology, we really need to separate our thinking into pipe body anomalies and seam weld defects. And we need a technology that can handle both of those, right? So what do we do about that? How do we find them? So there are two predominant crack detection technologies that I'll talk to you about today. If you've been in the industry for quite a while, you're probably familiar with ultrasonics. I'd say it's where everything originally started, beginning in the late 80s, early 90s. And then there's EMAT, electromagnetic acoustic transducer, which is a lot more popular with gas pipelines because of the obvious reasons we'll talk about in a moment, not needing a couplant. And I'm going to talk about both of those and just give you guys a little bit of the technology premise. Again, everybody's heavy from lunch. If I know Chris pretty well, I'm guessing it was either barbecue, maybe fajitas, or if he was having a really good day, he might have done lasagna, which means everybody's probably really heavy right now. So again, stay with me. When we talk about ultrasonics, we primarily talk about sending a signal into the pipe wall, an ultrasonic signal from a transducer, and then we're listening for reflections, right? In the more of the reflections we get, which are directly proportionate to the size of the flaw, the larger the amplitude is, the louder the sound that the receiver hears when it comes back from the pipe. And in very, very simple terms, it's a very well established technology premise, and it works extremely well. The real limitation is obviously that it requires a couplet. So sound waves, they attenuate in air. So when we put this in a gas pipeline, it becomes very difficult to use ultrasonics to measure cracks. When we talk about ultrasonic technology, I also want to take a little bit of time and talk with you guys about the detection thresholds, because that's going to be really important. When we look at ultrasonics, we're primarily talking about 1 millimeter in the pipe body or 2 millimeters in the longitudinal weld. And again, one of those things that we have to pay attention to when we talk about crack detection technologies is what our detection limits are in the pipe body and what they are in the weld. With regards to length, ultrasonics usually can detect fairly short flaws on the order of about 0.4 of an inch. And again, when you take a look at this spec in more detail, you see some other information such as the inclination and orientation limits down here. All of those important for understanding whether or not that given technology is capable of finding what might exist in your pipeline. And again, we're going to talk about that more in just a moment. We talk about EMAT, which is electromagnetic acoustic technology. EMAT has a couple of really nice features. Number one, the technology works without a medium, as we'll see in a moment. And it also has the ability to assist not only with crack detection, but also to deal with coating disbondment and coating identification, both of which are helpful when we talk about the very common problem of stress corrosion cracking associated with gas pipelines. So a lot of people are always interested in the coating detection or the coating analysis that comes with EMAT. So this is just a really good slide that demonstrates how that works. So when you look at EMAT, it works by generating, and again, I've got a slide in just a moment that will explain how it generates a signal, but it hears back. It generates a signal very similar to ultrasonics, and it listens for reflections from that signal. That signal will attenuate to a certain extent. What we refer to as the transmission signal will attenuate to a certain extent depending on what coating you have. And right here, this is a really good example of a pipe that had a series of FBE, tape wrap, and coal tar. And you can see very clearly how those signal patterns look distinctly different in the data that we evaluate. In addition, when we talk about transmission, we can also see where the pattern is disbonded. So for instance, in coal tar, where it's really common, if you suddenly get a large area that looks like this, where the signal attenuates, you can deduce that you have a coating disbondment there. And that allows us to both quantify the type of coating that's in a client's pipeline, as well as what the overall or general condition of that coating is. So the measurement principle behind EMAT. As I mentioned, one of the nice things about EMAT is that it doesn't require a couplant. Instead, what it does is it relies upon the magnetic principle. So if you induce an electrical current, and I am a structural engineer, I'm not a mechanical engineer. So I took one physics course in electricity, and that was more than enough for me. So I get real quickly outside of my limitations. But it works off of the principle that if you generate an electrical current within a magnetic field, that has the ability to create acoustic waves within the pipeline. And very similar to ultrasonics, we send those sound waves in one direction through the pipeline from a sender to a receiver. And this kind of shows you graphically what happens there. We listen for a couple of things. So for instance, if you have a flaw here in the pipeline, what will happen is a portion of that signal will reflect back to the sender. So EMAT works off of sending a signal, listening for how much of that transmission signal was received on the other end and how much was reflected back to the sender. It's a little more complicated than that because we have to get into frequency, wave modes, and other things like that in order to properly identify a crack or size it. But the principle works quite well. And again, the advantage is that we actually don't need a gas or a liquid medium in order to induce that signal into the pipeline. Right. When we look at the sensor setup on an EMAT carrier, so this is actually what one sensor setup looks like with a yoke, and you'll have a series of these that go around the pipeline in an EMAT tool. This particular technology is unique. This technology arrangement is particularly unique to ROSEN, and it's highly effective in being able to locate and size flaws. In every single carrier, you basically have a series of 4 sensors that are a combination of transmitters and receivers. So you have a transmitter over here, a receiver over here, a transmitter over here, and a receiver over here. And they send signals from transmitter to receiver, very similar to the diagram I just showed you. Anytime you encounter a flaw that exists between the transmitter and receiver, rather than that signal making it to the receiver, it gets reflected to the opposite receiver. And that allows the analyst to know that there's a crack there. The size of this window that you're seeing here is 40 millimeters, and that becomes important as we'll see in just a moment. You can also see that the cracks are, these circles overlap between the sensors, which is another really nice advantage of EMAT. Because when we look at the sensor arrangement around a pipeline, when we specify 100% coverage for something like a crack tool, we actually don't end up with 100% coverage. We end up with closer to 115 to 130, depending on the diameter of the tool. Okay. I'm going to talk just briefly about this because I mentioned that unlike ultrasonics, where you're primarily listening to the magnitude of the reflection or how loud that reflection is when it hits a crack, when you're looking at EMAT, you're looking at both the time and the frequency of the ultrasonic signal that was generated in the pipe wall. We listen to time because how fast it reflects back to us tells us something about where it's located within the pipe wall, as well as, in addition to that, what type of feature we're looking at. So, for instance, actual pipe body cracks that we're concerned with will send a different time signature than something like a lamination that we're less concerned with. In addition to that, we also look at the frequency distribution of the signals that come back. So a lot of times, if you're familiar with EMAT technology, you might hear about SH0, SH1, SH2 frequency modes. These are all related to what we like to refer to as the bass or the treble. It's basically the signal response characteristics of a given reflection. And the closer those get into the bass range, the deeper the flaw typically is. And again, so that's why I often tell clients, if they're familiar with UCD, they want to see the data in a similar arrangement to UCD. And that's actually very challenging because EMAT is unlike, to be honest, any other analysis technology or inspection technology that I've come across. It requires a high degree of background in the technology in order to understand and utilize the data to actually find flaws. When we look at the detection limits and what it is that you can find with EMAT, there are some distinct differences from ultrasonics. So in the pipe body, we have 1 and 2 millimeter depth sizes that are the minimum probability of detection. And those vary as a function of wall thickness down here, right? So EMAT deals very well in the range of 4 to 10 millimeters. When you get into the thicker pipe walls, the detectable flaw size increases. In addition to that, we also see the same distinction that we saw with UCD in the longitudinal weld area, where the minimum detectable flaw sizes increased to 2 and 3 millimeters. The detectable length is different from ultrasonics in that it's a bit longer. So rather than 0.4 inches, we're looking at 1.6 inches now. So again, other things to pay attention to when you get into the specification is the orientation of the flaws, as well as the ability to detect and size colonies right here and how that will be reported. So again, all these things are things that I recommend that you pay attention to and that you get involved with. So after you heard my presentation, you're like, I want to run EMAT. Where do I sign up? And I'm going to say, hold up. We need a plan first. I believe the best thing that you need to do is take a step back, understand why you're running EMAT, and let's talk about it. And that's where I want to get into what ROSEN refers to as the crack management framework. So the crack management framework really has its basis in fundamentally changing how ILI operators want to integrate and talk to the pipeline operators. I'm going to say the way that it was historically, if you look at how MFL data is treated, if you look at how caliper data is treated, the ILI vendor operates over here. They run the inspection, they finish the inspection, they hand the final report to the operator, and both of them go off and do their own thing. I'm going to say don't manage your ILI data this way. If you hear one thing from me today, if you're going to run crack detection technology, do not run your crack detection technology this way. You need to run it this way, which is we're together. We're part of a team. We need as much information to help us properly identify and size flaws to ensure that you get the best possible inspection. If you try and run this way, it will not result in as good of an inspection. I can promise you that. So the crack framework looks like this, which is boom and eyeful. I'm not going to walk you through every single one of these because Ryan told me roughly 20 minutes ago that I only have 30 minutes. Since I only have 30 minutes, we're going to focus on only the big data points. So let's start with data gathering and why that's important. Data gathering is important because if you decide not to heed my warning and you're like, Rhett, I got this, I'm going to put the EMAT tool in the pipeline and I'm going to see what it gives me, you're very likely to produce something that looks like this. right? And what this is, if somebody before me has not talked about limiting flaw sizes, this is a curve that tells you when you have features that are a concern to you in a pipeline, right? So when we look at this, features that are down here are happy faces. And, ooh, that's a bad happy face. Features up here, they are mean faces, right? And what happens is you run the technology and you get 100 and something features, and all of them come back with bad burst pressures. That leads to a very unpleasant experience. And a lot of times, if you're upfront, if you're gathering information beforehand, you understand the threat that you're going after, you understand your material properties, you can prevent this type of thing from occurring. So, and again, I've not had anybody that I know that's had this. I'm speaking for a friend. This has never happened with any of my clients. So, if you find yourself in the following situations, you've never run a crack detection technology. You don't understand the difference between Sharpie and toughness. You know the pipeline has a potential cracking issue for sure. Or you have never performed an in-field investigation for a crack feature. If any of these apply to you, ask questions and get help. That is the number one recommendation I want you to hear from my presentation. Get help. So, talking about defect critical size, why is that important? Again, you guys have heard a lot today on properties and loads and the importance of all of that and how it functions with crack size. The reason that that's important, and the reason that you need to really understand all of these, you need to understand your mechanical properties, and you also need to understand the loads that act on the flaw. Is there's two potential outcomes when you run a tool. And if you don't understand those properties beforehand, and you don't have a handle on it, or maybe you think that the guidance that's given in the mega rule is really good in terms of material properties for seam welds, you can end up with something that looks like this. And what I'm showing you here on the left-hand side is the dashed red line is the inspection tolerances for EMAT, right? So you can see here that in the seam weld, it's about 0.08, and then you get the minimum detectable length right here. And then I plotted your critical flaw curves also in this plot. There's a really big problem with this plot. It tells you that any feature that the EMAT tool finds is going to be in the unhappy zone. That's a problem, right? That basically means that anything the EMAT tool detects, you're going to have to dig on the basis of this. But it's got another big problem as well. This particular setup with this arrangement of properties can't guarantee that the EMAT tool can actually find your critical flaws, right? So if you're looking to run EMAT for something like ECA for MAOP reconfirmation, or if you really need to be able to justify the integrity of the line on the back of an EMAT run, this combination of properties and flaws is not going to do it for you. Where we need to get is somewhere closer to the right, where we have a better understanding of our properties, more realistic understanding of what's driving the flaws, such that we can ensure that flaws that are found by EMAT don't all necessitate investigation by you and can be responded to appropriately. So, another really important component before you choose to run when we talk about data gathering. So we've talked about, again, understanding your material properties and critical defect sizes. Another really important point is understanding previous flaws that you might be after, or understanding your threat. So a lot of times we'll ask the operator, what is the threat you're after? Have you done a root cause analysis? Do you have information that helps us understand? The lessons learned from those failure investigations are invaluable. It can help us understand whether we're looking at a brittle or a ductile failure mode. It can help us understand whether or not that flaw is particularly detectable, right? And so when we look at something like this, a lot of times you as a client will go to a salesperson and you'll send a picture and you'll say, hey, I've got cracking in my pipeline. This is what I'm after. To help you guys understand what we're looking at here, this is the axial position of the pipe, and this is the circumference moving this way. So what you're actually looking at here is circumferential cracking in the pipeline. When you go to the salesperson, they're going to say, yes, you can see this. It's a crack, no problem. You need to run EMAT. Hopefully, you talk to a member of my engineering team before you run the EMAT, because the engineer is going to look at this and say, nope, EMAT-C is not the right inspection technology for that. If you want to find it, we need to talk about an alternative means. And I can't tell you guys, at least 2 to 3 times a year, I have a client that's preparing to run an EMAT that we need to get in front of because the particular orientation or type of cracking that they're finding, either in terms of depth or in terms of orientation, isn't detectable by the technology that they want to put in your pipeline. And so, in the interest of making sure that you get a good inspection, you get results that are meaningful to you, we need to make sure that we put the right technology in the pipeline to find the feature that you're after, which means, again, understanding the threat that you're after, understanding previous failure investigations, and understanding the root causes of why those cracks are existing. And this is where I like to point out, this is all the work that should have been done before we actually get to the inspection. Historically, when we talk about inline inspection, people usually think of starting here, run the tool, then deal with the data. I'm hoping what you're hearing from me is we need to shift the paradigm. We need to understand the problem before we actually run the inline inspection, because doing that will allow us to actually appropriately characterize the pipeline, ensure that, number one, we have the correct tool selected for its objective, and that if we need to run other technologies to address that potential cracking, we include those as well. Again, I'm moving quick. This is because, again, I need to get through maybe 45 minutes of material in 30 minutes. Another place where we find ourselves offering significant help to operators is in the fields of immediate crack assessments. So again, if you've never run a crack assessment, I can promise you that you're going to get a report back that probably has a combination of A and B features. Most operators, the first time they see that, what's an A feature? What's a B feature? Do I need to do anything with the A features? Do I need to do anything with the B features? How many of the A features should I dig? How many of the B features should I dig? These are all the types of things that I recommend working with us on to help you ensure that you get, again, the most comprehensive use out of your data. We can help you do things like understand where the best places to excavate are to maximize the amount of information you get back, and help you also with the application of things like API RP 1176. All that to say, some operators will take the stance of, you know what, I'm just going to pig and dig. I'll pig it. Whatever flaws I get back, I'll dig. Every crack you give to me, I'm going to dig. That usually doesn't work well. It might work well the first time if you get 4 or 5 features. It's really going to cause you heartburn when you run into that line. That's a problem child, and there are always problem children out there. So, an additional component that you need to be aware of after you run the tool is, what are you going to do once you get into the field, right? And again, I know you guys have had a lot of discussion today on field verification. It's always easier than it sounds, right? So a couple of things, reasons that you should be working very closely with your ILI vendor is field support is critical. Cracks are not always visible immediately when you get out to the field. And a lot of times you might find something in the field that surprises you. And when you do, it's very helpful to have support there on the fly that can help you understand if you're in the right position. Number of times that we have to talk to operators that are in the field and help them understand whether they're on the right joint or whether they're in the right location of the joint happens numerous times a year. In addition to that, sometimes the operator finds something they're really surprised. The feature might be much deeper than they were expecting. Sometimes they find other below threshold features in the vicinity of the feature of interest. And it really helps to have an analyst there that can help answer questions about looking at other upstream and downstream joints. So sometimes when they get in the field, they find themselves suddenly being like, hey, based on what I've found, I'm really curious if I should dig a few more joints upstream or downstream. Should I expect to find anything? Or if I'm going to cut this piece of pipeline out because I want to do full-scale testing on it later, is there benefit in me taking just this 6-foot section, or should I go and take, maybe 2 or 3 joints out because they might have other features there? Another important thing is that inspection is an iterative process, right? And classification as well. A lot of people want to believe you just get a final report and you're done. I want to caution you against that approach. A lot of times when you're dealing with cracking, just because some of the challenges of the system or the challenges of the cracks you're finding, it can be necessary to go back and reevaluate and maybe reclassify the signals on the basis of what you're finding in the field. Again, with a process that's outlined very similar to what's in RP 1176. We talk about field verifications. This is a really good example. So after the first field verification, this is what was found. It's a fairly short feature, but it turned out to be fairly deep. And it had type B classification. Based on the signal characteristics that we got back from this type B classification, the client came back and said, hey, can you go look for any other features that might have a similar signal pattern but might be below threshold? We took that, went back through the line, found a group of features on the basis of other characteristics, not just a signal pattern, but we considered similar pipe vintage, similar coating type, and SCC susceptibility. We identified a few features. 2 of those features we found below threshold cracks right here. That again, they were actually deep, but since it was near neutral pH, SCC, very short, but very deep. But similar in terms of susceptibility and makeup to the original crack. So again, one of the benefits of working closely with your ILI vendor. Another area that we often get involved in is helping operators understand how to appropriately deal with the results of their inspection. So this is an example of a feature that we got back. And what they see here is a lot of cracking. And so it's immediately, hey, why didn't you classify this as a crack? This was a missed call. We need to look into this. How many features do we miss on the pipeline? When we start actually getting into it, what we found is that we actually had very shallow cracks below the detection threshold for the technology. And we're able to scale back and say, hey, both from an integrity perspective, these flaws were shallow, so not a significant integrity threat from the pipeline. And they're also below the threshold for what the tool is going to be capable of finding. But since we know we have some other corrosion type signals associated with it, maybe we can begin to use a different technique, looking at the signals in a different way to help identify and find these features. So I just skipped through a lot of material really fast. If you find this overwhelming, again, I want you to hear the message, which is get help. When you run a crack detection technology for your first time, get help. At ROSEN, we're here not just to give you the inspection technology, but to help make sure that you get the most from it at the end of the day. Crack assessments are complex, right? We do a really good job, but we can do an even better job if we have more information. The more information that you help give your ILI vendor, the better that they can tune their assessment to meet your needs. ILI is really good at understanding what's in your pipeline, but if we're going to do fitness for service, if we're going to understand how much time you have, we need good quality material data, which you've already talked about before, and we need defect validation, a lot of times using burst testing, if you want to comprehensively understand what the fitness for service is. And again, let's align on the front end and share data. Before we put that tool in the pipeline, let's have a plan of what we want to do. All right. So with that in mind, that's the end of my presentation, right on the dot for 30 minutes, and I will open it up for questions, Ryan.
Appreciate it on 30 minutes. And we did have hamburgers, by the way. Can you hear us? Okay.
So I think if you can hear me, Ryan, I see there's a question by Walbert, and it says, does it work for epoxy coating? We can correctly identify epoxy coating. We do not have the means to assess the what's the word I'm looking for, the quality of the epoxy coating. Because of the nature of those signal reflections, we can't do the same type of a coating analysis that we can with coal tar enamel or tape wrap. It's a good question. So Connie Trung asked, has ROSEN explored running UT and gas lines using another couplet? Yes, we do run ultrasonic and gas pipelines using a couplet, typically batched with diesel or something similar. It can be done. It's expensive, and it's also a mess. It's very challenging in the sense of if you have either one of the sealing pigs on the front or back end, lose that couplet, then the whole inspection goes to trash. But it can be done. It's much more challenging than running EMAT and usually less cost effective. Greg Story asked, what is the smallest diameter pipe that you can run EMAT on? We have 12-inch tools. I believe we have a few 10-inch tools either in development or that have already been put out.
Those are all the live stream questions.
Those were all of
Okay.
I just read off the comments.
You have any questions? Ashley, are those all the virtual questions so thus far? Okay. All right. Well, if there are no more questions, I really appreciate this. As you've seen, going back to that fracture mechanics triangle that a number of us have shown today, what we've kind of been building up is early on the first half of the morning, both Ken and Edgar, they were talking about how to improve your material property understanding. Now, Rhett's kind of given the other aspect of that with understanding, how to determine your starting flaw size. So now if there are no more questions, we are going to take maybe a break for a few minutes and get set up in the back because now we're going to have a lab tour. Ashley's going to try to set this up so we can see some demos virtually. So are there more questions before we kind of take a short break so Ashley can get the cameras and equipment set up? Okay. Well, I think there's a number of demos. We'll start doing this now. I think we're going to show Chantz Denowh. He's going to kind of show you some of our testing capabilities here at ADV. We'll spend some time chatting with Chantz on that. We also have one of our senior, technology guys. He has a spool of pipe in the back that we're going to show a demonstration of how EDM notch is laid out. And then I think we also have a new cleaning process from a company called Atmospheric Plasma, and they're going to do a quick demo as well. So stay online if you'd like to hear any of that story. And if you have to run, we'll be back after, let's see what time, in an hour. And then Casey Whalen from CSNRI will also, he'll give a discussion about composite technologies for repairing cracks. All right, so we'll take a quick break now while everyone gets set up. Thanks.
All right, you're good, Chantz.
All right, I'm live.
Yes, you are.
All right. Well, welcome back to the crack workshop. We're going to start first off with our first demo, or I guess you could call it a lab tour. Following this quick lab tour, we're also going to have 2 other demos. Cory Duncan with ADD Fabworks is going to be demonstrating how to install EDM notch. Following that, we'll also have our guest from Atmospheric Plasma showing us a new pipe cleaning technology. And so we're going to kind of move from one of these after the other in an effort to avoid this presentation looking like a scary movie with a shaky cam. We're going to be rotating the camera as we go and just kind of keeping stationary as we walk through this. So for our lab tour, I thought the first thing I'd do is we'll kind of start from the beginning of a project of when we receive pipe in either from the field or if we're buying pipe in from the mill to do manufacturer defects. And we'll kind of walk through the process of installing the notch, cycling on one of our pressure cycle pumps, either to failure or burst, and then into the metallurgical examination if it's required. So to start with, typically what we always want to do is we always want to try to test features that have been removed from the field. The best feature we can always test is an actual feature from the line. A lot of times, though, that's not possible to do because that's a feature we want to keep in operation. We don't want to have to cut it out. So here in the lab, what we can do is we can recreate those features. And so the process that we do that, especially when we're looking at pipeline cracks, is through using EDM notches. And so Cory will be demonstrating the actual installation later, but this is what the setup looks like. So for example, we bring in 12, 14, 30-inch pipe from the field. Our first step, if we're looking at either pipe body or seam features, is to locate the location of the notch. For a pipe body notch, that's pretty easy. But when we're looking at installing a notch into the ERW seam, our first step is to identify that seam location. And so we'll do that by polishing the surface of the pipe or the ERW seam and then etching it. And like we saw in Ken and Edgar's presentations earlier, when you etch that pipe, that seam really pops out of the etchant. And you see that exact same thing here on the pipe surface. That after you do that etchant, you'll see that seam pop out of the surface of the pipe. And it's very clear to see. So once we have identified the seam, then we can go in and install our EDM notch. And so one of the challenges, especially when we're looking at those seam features that are in that bond line, is making sure we get that notch right into that bond line. And so from the outside of the pipe, after we identify it, that's where we install it. Now, there's no guarantee that that seam isn't going to change direction once we start going in. That's where post-test, what we can do is after we've ran it to fatigue or we've burst the pipe, we can section it, polish it, take it into the microscope, and really see where that crack landed, if it was in that ERW seam or not. So that's the first step. After we get the notch installed, we'll install end caps. Here at ADV, we do that internally. We have our fab shop that you can probably see here in the background. Get the end caps installed, and then we'll install it into one of our pressure cycle systems. And so this is just one example of our pressure cycle pumps and chambers. And so we've actually have 3 to 4 of these 5. Yeah, you lose track. I think we have 6 now. 6 different testing chambers that we can use for different sizes of pipes. So inside this chamber right now, we actually have 2 pipes that we were fatigue testing. Actually, we stopped those earlier this morning just so they wouldn't be running in the background of the presentations. And so on those 2 pipes, we have different instrumentation. Actually, we have both weldable strain gauges and clip gauges that are monitoring cracks and crack growth. Connected to those, we have 3 different cycle pumps here at ADV that can run all the way up to 3,000 PSI. All 3 pumps come in basically 3 different sizes depending on the pipe size that we have. The 2 pumps that you see here are best suited for about 20-inch or below diameter. They can do higher diameter, but then your cycle times are just getting really long because they have a lower flow capacity. Behind the camera, which you can't see, is our largest cycle pump, and that's where we will cycle anything up to a 36-inch diameter pipeline. And even with that pump, with a 36-inch diameter pipe, we're cycling at rates of 5 to 6 cycles per minute. With our other equipment, we usually target that 6 to 8 cycles per minute range. And so, throughout a day, that's about 10,000 cycles a day. And so as we get to these projects, we're looking at, need hundreds of thousands of cycles to either generate cracks or to fail cracks. We can do that with these cycle pumps in a relatively short period of time. So after we've got the sample installed, we got hooked up to instrumentation, we start cycling. We can monitor the crack growth with our data acquisition system. So it might be hard to see all the way back from the camera, but real time here on the computer, we're plotting the number of cycles versus that crack opening displacement. And so as we're cycling, we can see real time that crack opening displacement start to increase. And so in the case of an EDM notch, when we're pre-cycling to first generate that crack, we can tell when that crack has just started to form. If we're running into failure, we'll just keep running the sample and monitoring that crack growth all the way to failure. If we're looking at a situation where we want to stop that crack growth to say at 40, 50% crack depth, so that we can take it out, then either perform a burst test or install a repair to test the repair technology, we can do that. And we've gotten very good at that. As we run more and more samples, especially to failure, we can get a very good idea of the number of cycles it takes or that crack opening displacement required to generate those cracks. So for example, like for the JIP that Sergio was discussing earlier, I think we have 50 samples. I can't remember how many now. They're all running together. 50-some samples where we're going to be generating those cracks. And so each one of those samples, we're installing this instrumentation so that we can monitor it real time so that we know once we stop this pump that we have a crack formed at the base of that EDM notch. So that they're repairing an actual pipeline crack and not just a notch itself. So at this point, either we run it to failure, we stop, we connect one of our other pumps, we can perform burst tests in these chambers. That really takes us to the end. What we won't be able to see on the live stream, but we do have some failed samples on the other side of our bending beam here that we can take a look at. And you can see what those EDM notches look like after the pipe has been failed. So moving on from looking at pipeline cracks, one other type of crack that we can test is circumferential cracks in girth welds. And so you see last time when we're talking about strain capacity of girth welds. And so when we're looking at that, what we're looking at is large deformations, things like soil subsidence, where we want to know what the straining capacity is in the situations. And so for that, we can use a setup like this, which is our 4-point bending beam. So in this 4-point bending beam, we can do anywhere from 10-inch diameter pipe all the way up to 30-inch diameter pipe, up to 3 million foot-pounds. And so operation of it is very simple. You can see on the ends, we have the green hold downs that hold the pipe in place. In the center, we have 2 hydraulic cylinders that are rated to almost 500,000 pounds. Set the pipe in there, start pushing up on those hydraulic cylinders. They contact the hold downs, then we place the pipe into a 4-point bend. We like 4-point bends because in between those 2 cylinders, the pipe's in pure bending. There's no shear forces involved. So the best simulation of a soil subsidence situation or a large strain capacity situation where that girth weld is moving. So what we can do is we can test girth welds. We can also install EDM notches in those girth welds or in the heat effective zone. The common problem is the heat effective zone softening, especially when you start looking at higher strength steels. When they're welding those girth welds, they have softening in that heat effective zone. That's where your cracks can form. That's where you can have problems. And so we can install both internal and external notches in that heat effective zone. Other things that we have in the background that we won't have time to show you is we also do a lot of elevated temperature or low temperature testing. Back here in one of our low temperature test chambers, we can go down to -50 degrees Fahrenheit. We just did a 30-inch pipe test only a few weeks ago where we took it down to -50 and performed a burst test. On the other side of the spectrum, we can go all the way up to 300 degrees Fahrenheit, maybe even a little higher. We haven't had a chance even to push our newest oven, which is behind the camera. So if we have anything where we want, for example, we want to test a composite repair at an elevated temperature, we can put it in one of these test chambers, heat it up, hook it up to a cycle pump, and test that in fatigue. We also do a lot of other non-metallic testing of non-metallic or spoolable pipes. And a lot of times those have very temperature dependent properties. And so we'll use these test ovens to test those products as well. But with that, Ashley, I don't know if people are asking questions in the live stream or not, but I can take any from the live stream, or if anyone else has any questions that I can answer, I'd be happy to.
I have a question for the low temperature testing capability. Have you ever examined any, or is it contemplated maybe in the JIP to test at low temperatures, the potential for crack arrest of a cleavage-related value from under?
Yeah, not in this program. I tested composites at -40 on the pond, but then so. I know that's something certainly our Canadian brethren would like to see.
I could repeat that if you want me to. Yeah, sure. Yeah, the question from the from Ken was, how are we in the JRP? Are we considering testing any of the composites at low temperature, reduced temperature? Not with the JIP, but as Chris was mentioning, it has something that we've done in the past. One other thing we've done testing wise is we also can chill a sample before a burst test. So we've had situations, one I can think of is we had SEC where the line was operating at 40 degrees Fahrenheit. And so before we performed the burst test, we chilled the pipe down to 40 F and then performed the burst. So those are other things we can do as well. Okay. Thanks. All right, so if you're on the live stream, bear with us for a second. We're going to shift gears, and Cory's going to give us a demonstration of installing an EDM notch.
So as Chantz mentioned, my name is Cory Duncan. I do oversee most of the manufacturing that we do here, machining, sample preparation. And one of the things we do in-house is install the EDM notches. Just a quick rundown of just a base level understanding of how we get started. We've obviously got a fancy machine here. We've got you've got a mounting block. The center section is a hydraulic cylinder. We've got about a 1/2 inch of travel up and down into the pipe. If we run into a situation where we're in the throat of a T or a valve or a flat piece of plate, we'll actually get back here in our CNC machine and machine different variations of these blocks to give us a 15-degree angle so that we can maintain the precise nature of what we're trying to cut into it. Most of the notches that we do here in the lab use a 3-inch long electrode, and we'll do 2 or 3 inches of length in the electrode at various percentages of depth based on the pipe. Some of the materials that we use are a graphite material. I've found that using copper tungsten material on another little small machine we've got will yield a really, really thin notch. I've gotten down as thin as 4 to 5 thousandths on the electrode. You end up with 2 to 3 thousandths of overburn on the width of the electrode. So, you know, we can get down in the 8 to 9, definitely the 10 thousandths width range on these notches. We've been cutting a lot with graphite just because it's easier to use. We can sand that down. We can adjust the shape. We can do whatever we need to with regards to the requirements of the notch that we're cutting. But the process of EDM is electronic discharge machining. So you basically have a DC voltage that's coming out of the machine. You've got a positive charge that's going to the electrode. There's an acrylic rod that goes between this machine that actually isolates the head on the end of the hydraulic cylinder from the base pipe. We negatively charge the pipe, and then we've actually got a dielectric fluid that's flowing now that flows in between the pipe and that electrode. And as we increase the voltage, the DC voltage on the machine, it causes a breakdown in that dielectric fluid, which allows that electrode to spark into the pipe and thus eroding the material. The good thing about the EDM notch that we put in here, there's no work hardening that you'd find if we tried to cut a notch with a mill or with a cutting tool or something. You don't have any work hardening in that area. And because of the dielectric fluid and the small amount of DC voltage that's going into the sample, you don't have a heat affected zone. So you're just lightly eroding the material out, and depending on the size of the electrode, some of them are take a painstakingly long amount of time. But the notches are one of the primary things that we do here with the tool, and it's a pretty simple setup. There's just a lot of moving pieces that go into getting everything to this position. Depending on the material, I found a lot of times too, if some of the older pipe, some of the newer pipe, I've cut some notches in some varying materials. We've got the ability to adjust the voltage range from a low, medium to a high, and we can also adjust the frequency. So this machine's actually oscillating on off with the DC voltage that we're applying, and we can increase or decrease that frequency threshold to cut better. Obviously, the higher frequencies, the higher powers, you're going to lose more on your electrode. If you run a lower power and kind of play with the frequency, you got a lot longer electrode life and cut a really clean notch. You minimize the overburn. And this particular tool that we've got is actually calibrated to the cylinder that we have. So I've got a multiplier that if Chris and the guys tell me that we need to go, 201 thousandths deep on a notch, I've got a multiplier that I can do some math with that 0.201, and it tells me what my readout needs to be on this particular indicator. So if it's 201 and we need to go, I may be going to 1.069 on this indicator, but it's simply based off the area in that cylinder and how much displacement we get with a certain amount of fluid travel. But other than that, I mean, I've got everything set up here. We've got the dielectric fluid flowing. I've got about 1.5 inch long electrode in here. It's about 10 thousandths wide. And I don't know if Ashley can get in here and see, but as we start engaging, if y'all want to come in and look, we can look after the live stream if any of y'all want to see it. So you basically start, as I start engaging, you get that spark starting to jump across that dielectric fluid, and kind of ease into it. I just barely started this notch yesterday when we set everything up, and I base everything. You really can't see it here, but I've got an indicator that's right now showing 40 volts DC, and we generally run that down to where I can run about 20 volts DC, and that's high-grade kerosene too. It's just $20 a gallon kerosene that's flammable. So usually when you've got flames going, it's either a good social media post or I'm giving it too much. I'm giving it too much juice, but really looks good in slow-mo. But we're basically, going through, and the deeper you go with a notch, you wind up with more dielectric fluid in there. I could dam this up. There's people in the industry that'll take and wet a paper towel. They've used silly putty, Play-Doh, really whatever kind of dam you need. I've 3D printed some dams on our 3D printer, stick them down with some fast set RTV and take a razor blade and clean them up. But for demonstration purposes today, the flames are cool and you can see the sparks. So, I mean, you basically sit here and just, you know, as you gradually increase the position, this is just a syringe essentially that's got a calibrated readout or digital readout on it. I'm pushing .3 brake fluid and engaging the cylinder. You know, the average notch setup, start to finish and everything, 30 to 45 minutes probably by the time we get everything laid out. And generally the guys in the lab will go through, sand everything, etch everything, find the bond line, mark it, write the credentials on the pipe, and then me or one of my guys will come in and actually install the notches, update the test plans and spreadsheets we've got in the shop, and I can usually hit these notches within about a couple thousandths of what they're specking out based on percentage. So we'll actually come through here with a UT meter once all the grinding's done, measure that location, take an actual wall thickness, and we'll go to a percentage based on the actual wall in that location. And obviously, you know, when I stop giving it fluid, that notch will, you know, everything will just quit running. And right now, that's telling me that there's still contact, you know, or a little bit of pressure contact between that dielectric fluid. Once it quits, we're pretty well done. We'll flip the machine off, retract the electrode so we don't cut any more material, you know, coming out of the notch. But we've had the opportunity to cut a lot of different shapes. For the guys that are here, I've kind of set out an assortment of different electrodes that we've used to make wall reductions. Some of the stuff Rhett was talking about, you know, there's opportunities to make calibrated features for calibration tools to put defects in that simulate corrosion, that simulate cracks, that simulate gouges. We can do a lot of those and make a lot of different anomalies in the pipe that simulate real life scenarios and try to be able to let the guys like Rhett and Rosen and them be able to pick up on, okay, we're looking at a notch, it's this deep, it's this size, it has this surface profile, and be able to see that in inspection. But other than that, that's a 1.5 inch long, 10 thousandths wide notch. And if anybody's got any questions, I'd be happy to answer the easiest ones.
Big project with you. What's the biggest machine area that you
The biggest one that I've done with this particular machine was roughly 1.5 inches. What was that? Around 40 millimeters. So about 1.5 inches in diameter. You know, the smallest I've done, you know, small size is actually the EDM notch width. We've done some 5 millimeter rounds. We've done some rectangular ones. We've got some square indications that you can put in. Really any shape. I mean, I could take that square block and put my initials in it and actually go down into that pipe, and it's going to push that CD profile down into the bottom of that pipe. So there's been talk with some engineers, some clients about getting creative with different shapes at the bottom of the notch to see if you can get cracks to propagate in different areas. But generally, we'll run these notches. I can take a square electrode and cut, you know, on an average notch that's 80 to 100 thousandths deep. When I come through, the corners naturally round off on the electrode. You've got a little bit of light wear on it, but it gives you a really good clean radius bottom, and it's extremely repeatable. You know, so as long as you do your homework and you set the electrode up right, you put the block in, you know, everything is machined to where it's level, you know, on multiple planes, and we're pretty painstaking on leveling everything up, making sure we're square to the tool, square to the pipe, and the devil's in the details. I mean, we just really have to go through and set everything up. Screwing on this handle is pretty easy, but that's EDM notching in a nutshell. So, any questions?
Good demo.
Good deal. Appreciate it.
Then we are going to go ahead and go over to. Yeah, I'm going to go right.
Got your video too now.
Yeah, hey, we're still on there if you want to know if we're going over. Yes.
So again, we're going to drive over to Atmospheric Plasma Solutions and do a demo with Jeff.
First of all, I want to thank Chris and the ADV Integrity team for allowing me to come in today. My name is Jeff Pavelka. I'm the Plasma Blast Global Sales Manager for Atmospheric Plasma Solutions. And I'm here to demonstrate to you today the Plasma Blast 7000M. The instrument itself was originally developed for the Department of Defense. So that's where the actual technology came out of. The Department of Defense's biggest problem was they wanted to be able to remove coatings from critical structural areas like structural welds without using any type of grit or type of chemical. And they wanted to be able to do that in very, very tight spaces. So if you go onto a weapon system like a battleship where you have to actually go down into a port or down a ladder, they needed something that's very, very portable. The PB7000M, the other thing that they wanted something that did not hurt the actual substrate at all, did not degrade the substrate, did not do any type of damage to the substrate whatsoever. And also they needed something that created additional adhesion to the substrate so that they could recoat afterwards. So the critical thing is a person in a weapon system would go in, they would remove a critical coating over a structural weld, they would do an NDT test, and then if that NDT test on that weld was good, they wanted to be able to recoat it. So from that standpoint, we wanted to also take the system and commercialize it, and we wanted to actually get it out into the actual commercial market. And we thought that the pipeline industry would be a perfect place for that because of actually working over cracks and over leaks areas where you're not actually damaging the substrate, but also you're creating additional adhesion for non-metallic repairs. The actual instrument itself runs off of air and electricity. That's all you need to actually run it. You can run the cables as long as you want. I have a plasma pen right here that basically weighs less than 1 pound. It's a lot different than a grip blasting system in that there's no feedback. So from an ergonomic standpoint, it's really, really easy to use, and it's actually easy to use, easy to hold. You're going to hold it just like you're writing with a pen or pencil. Okay. Safety equipment that you use: welding gloves, standard safety glasses, and if you're in a confined space, hearing protection, just standard hearing protection. The interesting thing about a plasma beam is that it does not give off any type of thing that's going to irritate your eyes. So again, a standard pair of safety glasses is perfect for that. The beam itself, so not like a cutting torch. I don't get any residual heat from the actual beam, so I can actually work in close proximity to somebody else. So if somebody else is using this instrument as well, I can work in very close proximity and not have to worry about any type of residual heat or anything like that from that. The actual thickness of coating, it can take off, there is really no thickness. You can take off layer by layer. So we've done stuff up to 500 mils in thickness. We've taken off actually asphalt, actually off of roadways and all kinds of stuff. So the way this actually works is the organic in the coating is turned into carbon dioxide and water vapor, and the inorganic is turned into dust. So that's how you were going to basically vaporize the coating itself. All right, you guys want to see it in action? All right. So I'm going to put on my gloves here, and we're going to take the coating off. This coating here is a fast clad coating. It's a marine-based coating. It's a Sherwin-Williams, so it's a military system-based coating. So with that, you can see that I just coating off that weld. And the that is, I can go right back and touch it with my hand. Okay? Your heat right now, your heat temperature on that's probably maybe 100 degrees Fahrenheit. It's very cool. So most of the heat, residual heat, was lost in the actual vaporization of the coating. So probably 70% of all your heat went out into carbon dioxide and water vapor. So you can see I didn't damage the substrate at all. I didn't do anything to that weld. So now if I went in and did an actual NDT check on that, I check it if the weld's good, I can recoat. Again, I not only have I not damaged the substrate, have also created significant additional adhesion in chemical adhesion, in that it's different from mechanical. We're not changing this profile of the surface. We're creating a chemical adhesion, so we're energizing that surface so that again you can recoat and move forward with it. And I'll do that hole up there too, so you can see a little bit more of it. So that gives you a little bit better example. You can go over that hole, and again, since I'm not damaging the substrate at all, if this was a leak in a pipe, if I didn't know exactly what was going on with this actual leak itself, I'm not degrading that area any further than it already is. So I'm not the critical thing here is I'm not damaging the pipe any more than it already is from corrosion or environmental factors. So you're doing, and again, you're adding additional adhesion to it.
So Jeff, we had one of my client friends in Canada ask a couple of questions. One is it intrinsically safe and it can be used in the hydrocarbon gaseous environment? And then the other is, does it create an anchor profile?
So is it intrinsically safe? It is not intrinsically safe to means C1D1. It is not going to meet that C1D1 classification. The reason being, you have an open flame. So you're going to handle it just like you would if you were going to weld on a pipe, or you're going to use a hand grinder on a pipe. So typically what you would do is probably pull, like, I think they call it a hot permit. You'd probably pull a hot permit out there, and then you would actually use this tool. That's the way I would do. That's the way I would actually use it. Anchor profile, no. We are not damaging the substrate. So that an anchor profile would be a mechanical profile. So whatever you have on that surface, that's what you're going to have. That's the real critical thing. If you have aging assets in the field, that's the thing that I think is the most unique about this tool, is that you can go into a crack or a leaked area. You can basically remove the coating, remove the rust around those areas without damaging it any further. Examine actually what you have there, and then you've also created that additional adhesion. So then you can go back, and when you reapply your resin or your wrap, it's going to basically bond a lot better. We've done some pretty extensive dolly pull testing with clock spring in the downstream industry, and on typical like heavy rusted carbon steel type substrates, we've gotten up to 6,000 psi. Where the mechanical stuff goes at about 4,000 psi. So we can significantly increase, and even if you grip blast and then you go back over with plasma, you can increase the adhesion even that much more. So around girth welds and things like that, this could be good for that too.
Cool.
Okay. Does anybody else have any more?
Any questions from the audience?
Can you get it in a backpack?
Right now, this is what we have.
Joe's pretty strong. You probably better.
Yeah, you can.
How much
Sure.
are those? Do you sell, rent, or?
We lease them. They're about $4,000 a month. We lease them. We'll come out and train you guys for free. Get this thing going. We're looking for people to work with the tool, and we're very excited working with Chris and his team to actually implement it in the midstream and really I'm thinking cracks but there's could be a lot of other applications that as people start using it in the field, they can actually come up with other things as well.
You still have PSM facilities?
PSM facility.
Processing. Yeah, basically, where you got really cramped areas, right?
Oh yeah. Like confined space.
There you go.
Confined, yes. Yeah. So again, what you would want to do is, the military does that a lot. They actually go into fuel tanks and things with it to actually clean. The military does a lot of stuff with epoxies and with certain types of adhesives in confined space, where they have to remove those adhesive areas. They have to remove the hooks and things inside those areas. And you can actually do that.
Confined space access.
Right.
Yes, you would have to.
Like tanks, right? I go inside a tank and clean up the floor. And
Yeah.
a specific area I want to look at. This is not going to damage that.
That's correct.
Instead of a sandblaster, make a bunch of mess.
Yeah.
That's correct. That's correct. So,
Yeah, you're grip blasting, you clean it up.
when we first rolled this out commercially, from the military side, the first industry that picked this up was the renewable energy guys in Europe. And the reason they picked it up was because they had all epoxy coatings on wind turbines. And it was a clear epoxy coating on a wind turbine. And so they had no filler, so they had no dust. So when they heard that we changed an organic to carbon dioxide and water vapor, you have nothing. I have no filler in my coating. I just want to remove that epoxy, clear epoxy coating. I don't have any grit. I don't have any chemicals. And now I'm changing, now that the only thing I'm getting from that is carbon dioxide and water vapor. So it's very environmentally friendly. So they just, yeah, they took off everyone we had on our shelves. They took them in for the wind turbine market. So that's that story.
You kind of answered his question, but Fan is back, and he said, "Will the chemical vapor be harmful to help for the person in the ditch doing the work?"
No,
So perfect.
it will not be.
Awesome.
Do you have other attachments where you can blast a bigger area at once?
No, we are working on other things, but this was initially designed as a precision tool. So a person could actually go over a structural weld and go right along that weld. They wanted something you hold just like a pen and so they wanted something where you could literally just go right over that weld in a precision environment. And again, take off when you're looking at structural welds on weapon systems, you take off as little as you possibly can, because if there's nothing wrong, you got to reapply it. And so they've got guys just down the way doing those types of operations.
Theoretically, you could have a wider.
Yes.
I think of like corrosion under insulation applications. I'm not sure if anybody's ever approached you.
Yes, they have, actually have.
I mean, that's always an issue is how you remove that safely and control.
Mm-hmm.
Because you almost need an array. You and I talked about you have an array and you can just cover a water area.
We actually did a test where we put 3 of these together, and you could hold it with your hand, and it will just take that coating right off of there in less than a minute. The thing is, we want to watch residual heat. So we're saying we're not damaging the substrate. So when you get 3 of these together all going at the same time, that's the further testing you have to do, is making sure you're truly not damaging anything. Also, this is we've had several companies deploy this on robotics. So we've actually, in one of the tests we did, they actually had 29 of these in a row on a robot end effector, and the robot's doing this with it. And the robot obviously can, his positioning is plus or minus 0.003 of an inch, so he can really quickly move. And that actual application was taking off individual layers of coating. So it was taking off an organic coating over an inorganic coating, and you're not damaging the inorganic coating underneath because the positioning of the robot's so accurate.
How does that flame come out?
This flame here is about 100 degrees C. Yeah.
So how big of a tank do you need for blasting?
This guy here is the actual air pressure I'm running here is 90 PSI, 3.5 CFM. So I got a little teeny air compressor out there. It's about 40, it weighs about 40 pounds. It's not a lot. It's not a lot at all. Actually, the actual tank itself, if the compressor can keep up, I don't need a residual tank. As long as it can feed me 90 PSI at 3.5 CFM, I don't need any residual tank at all. And the power, you're pulling about 3,000 watts on this one. So I think it's about I think it's a little bit more than an actual high-end hairdryer is what I'm actually, from my power consumption standpoint. So it's not a lot. It's not a big power. It doesn't require a lot of power. It doesn't consume a lot of power. And again, that was the critical design aspect of it. It had to be portable. You had to be able to deploy it in the field. Somebody had to be able to carry it, and you had to be able to take it anywhere. That's why we think the pipeline industry, where you have to go out in the field and deploy something. And if you don't want to deploy large grit blasting equipment and have to do that, if you want to look at something, this is a great tool for something like that.
Or servicing, if it goes down, say I lease it and I'm out in the field for about a month, it goes down, take long to service it, or just kind of slap on the new parts?
No, this is the same thing. It's been designed to be it's completely sealed. It's CE certified, so in the European market, everything had to be sealed. So here, completely sealed, on computer automatically monitors your power consumption, and there's only have 11 standard error codes, so it'll tell you what's wrong with it. Like, you didn't hook in the airline, you don't have the right power going to me, that type of stuff. So it's very little things. The other thing is, if you work with us, we also have a drop ship program. So if something goes down in the field and it's critical to you, we get you another one. That's
I'm
it.
sitting there down the hole.
We FedEx you another one, and you just send us back the one that's not working. We're not going to mess with having to repair and all that type of
Someone
stuff.
out there, now I'm waiting around.
No, no.
Got a bunch of crew waiting around.
No, when you deal with the DoD, you learn how to FedEx critical stuff real quick because they don't wait on anybody.
Right.
They're not waiting around. All right.
Good job.
All right.
Thank you.
Thanks, guys. Really appreciate your time. Thanks again, Chris, for letting me do this. Really appreciate it.
Going next.
30-minute break. Okay. I'll take your mic. Thank you. Okay, so we're gonna, I guess, Ron, we're taking a break for 30 minutes.
Yeah, 30 minutes.
Okay. We're good.
has been completed already. Most of that's a focus on seam welds. We have crack-like features growing in the seam welds. Cool. All right. There's my title. What I just talked about. All right. So why would you even consider using a composite repair on a crack or crack-like feature in the first place? There's a few bullet points here, just a quick list on the benefits of composites in general. Composite repair can remediate that crack or crack-like feature without disturbing the pipe, right? You don't have to shut it all the way down. You don't have to drain it or empty it. You can still continue operations to some extent, and you can do that repair like you would go out and do just about any other normal repair. And this one maybe is controversial, but when you run an ILI tool through the pipe, the composite doesn't really show up. So you can still see how that crack looks, if it's still growing, if it's being stable. It doesn't take away that like some other technologies might, some other repairs could. But maybe most importantly, the composite provides the same benefits for why you would normally use a composite repair. You can go out there, you can do the installation. If you have a crew trained in using the Atlas carbon fiber system, they can repair corrosion, they can repair a dent, they can repair a crack-like feature, and the process doesn't change much. So it's pretty quick and easy to learn, doesn't require a whole new training or anything like that. But last 2 points, right? You don't need to shut down operations, and there's no hot work involved. You're not welding, you're not cutting, you're not doing any of that stuff. That's really a big reason why people like to use composite repairs in the first place. So keeping it very general here, since no one else talked about composites yet, how does a composite repair work? Well, when you have damage in your pipe, this is just a picture of a corrosion defect. You have stress that goes through the pipe when you pressurize, and if you are missing some wall, you end up with higher stress loads. If that stress load is too high, you end up with a failure. So what a composite does is when you put it on and you have that load transfer filler material in it, it lets that stress transfer out of the pipe and into the composite, so it's stress sharing between the composite and the pipe. So really what a composite does is it relieves a lot of that stress in that pipe underneath. Now, if you're putting it on at higher pressure, it may not be doing as much at those pressures and lower, but if it does increase in pressure, if you end up with more wall loss, if it's internal wall loss scenario, that additional stress gets transferred to that composite, or it gets shared with the composite as well. Now, when I mention a composite repair system, I'm talking about the entire systems. This includes considering what is in the pipe material itself. Then you have the filler material, you have an adhesive primer that is used to bond the composite to the pipe. It prevents further corrosion occurring on that surface, kind of like a coating. And then lastly is the composite layup that everyone talks about all the time. So with that very basic description of composite repair, I want to spend some time to talk about what composites have done for crack and crack repair reinforcements right now. So the first real program that looked at composite repairs on cracks was initiated in 2015, where a company came to us and they talked with PHMSA and they talked with a whole bunch of different people, and a test program was generated to see if composite repairs and some other systems could be used to reinforce a crack. So the first kind of testing that was done, some samples did come from the field, other samples were created using EDM notch technology, which was demonstrated earlier. And all these EDM notches are cycled until a crack is initiated. So the first test program, though, we just want to see if composite repair was even a realistic idea. So we put on a whole bunch of layers, pressurized it, and we ended up bursting most of the samples outside the composite repair. In fact, a lot of them burst at the end caps at very, very high pressures. So we knew a composite repair can prevent a crack from, blowing at the crack area. So it was worth looking into. So the next phase there was to actually, I'm gonna take a step back here, was to kind of optimize the system. So we put on layers at 12, 18, 24, 36 layers, and you kind of saw what the results were. It ended up looking really good at 33% deep cracks. We could fix those with about 24 layers, actually with 18 layers, and it looked really good. But if we went too high, 75% deep crack in this test scenario, it didn't work out so well. It took a lot of layers to get significant improvements. So I only say that to warn that composite repairs aren't a magic bullet. They won't fix everything, as Sergio mentioned earlier today. But composite repairs do have a place, and in some situations, they do work very well. So the success of this test program led to several dozen repairs in the field on this specific line. And generally, we were looking at 24 layers of the Atlas repair system on up to a 3-inch long crack, and each repair was about 3 foot long. But this spurred an additional test program, JIP, where we looked at 15 and 50% deep alongside several other composite repair companies. Now, one thing we didn't do on the previous test program was look at the cyclic effects on cracks and crack propagation. So here we did wrap these samples, 15, 50% deep, but we focused on cycling. So we actually cycled, if the pipe survived that long, up to 250,000 cycles. And you can see some pretty interesting results. I took the table that's in that JIP report and kind of cut it down to just look at the Atlas system. But the first thing I want to point out, for the 15% deep crack, the cycle of failures increased from 80,000 cycles to about 200,000 cycles using less than 1/10 of an inch of carbon fiber repair system. So that's a significant improvement. It was 6 layers. That's a small crack, maybe not a big deal. But when we move on to that 50% deep crack, we increased the cyclic fatigue from 2,000 cycles to over 250,000 cycles. So that's a dramatic improvement. And here we used over just a 1/4 inch of carbon fiber. So we can get some pretty significant results with carbon fiber or with composite repair systems. And since that test was completed, a lot of other owner operators have come to us specifically through ADV, through other channels, and a lot of them have been doing their own test programs to validate their pipes, their situations, and a lot of that information isn't something we can publicly share at the moment, although I'm trying to convince people to be more open about that data. But it's working. We haven't really seen anything that says a composite repair should be avoided at all costs, except in those extreme areas where we're looking at very deep cracks, maybe it's already close to through wall. So looking at these test programs, we wanted something that was more than just a pass-fail, like composites can do it, maybe in this case, maybe not, who knows. So we worked toward developing a model that we could use internally. So the general hypothesis we used to follow this, well, we know that a installed composite will reduce the amount of stress that's in the pipe, right? That's what I talked about earlier. Composite eliminates or reduces the amount of stress that's being carried by that base pipe. And if we know how much it reduces and we know some of the fracture mechanics properties of that pipe, then it's reasonable to assume that we can use fracture mechanics modeling to estimate the new burst pressure of that pipe. Going one step beyond that, it's looking at the cyclic fatigue data. So if we know how much stress we're reducing every cycle, then you can take that information and reevaluate when that crack is going best. That helps you determine if it's a tear repair or if it's good for another 200 years. You could probably call that permanent, right? So using that information as a baseline here, I just kind of want to walk through it shortly. So again, I mentioned when you pressurize, that stress pushes up against the pipe. That pipe has to expand radially outward. If the composite is in the way, then it gets into a stress sharing scenario. So this is actually a fairly simple model. There's a lot of research out there for how that stress gets distributed between two systems like this. So I'm not going to spend too much time talking about it, but essentially we could bring it down to a modified Barlow's formula. Instead of P is equal to 2ST/D, I split it up so you have your load inputs on the left, PD/2, and your material response on the right, with the material response being broken up into the pipe and the composite. Then you can play some math games, set the stresses in terms of strain, put your modulus. Then you can solve, basically the pipe can't expand more than the composite expands, so you can set some terms equal. And ultimately what I wanted to do is solve it in terms of an equivalent pressure. So this equivalent pressure is something that I've been utilizing just as a way to combine the stress distribution into fracture mechanics. Essentially here, what I'm saying is, if you have a pipe, for example, that's running at 1,000 PSI, it has a certain stress level in the pipe itself, right? And if you put a composite on top of that pipe and you're running it at 1,000 PSI, the equivalent stress load in that pipe is reduced because the composite's taking some of that load now. So maybe let's say it had 10,000 PSI stress loading, you put a composite on, it drops down to, 5,000 PSI or something. 10,000 PSI, we'll do half. And then if I wanted to model the equivalent amount of pressure without a composite on it, I would bring that pipe pressure down half, right? If you have half the internal pressure, you have half the stress load. So that's kind of mimicking the effect that the composite does. So using the composite repair thickness, the stiffness, the installation pressure, and a couple other variables, we come up with a equivalent pressure value that we utilize. And then that's kind of what I just mentioned. This is kind of the nice pretty format here. It's just the ratio between the composite, the pipe, and what their stiffnesses are. But we use that equivalent pressure, and we can plug that into fracture mechanics models right away. One distinction I want to make here, though, is when we're talking about crack or crack-like features, right, you can have manufacturing defects in seam welds that may not be cracks, but your ILI technology may not be able to pick that up. Either way, when we're doing this model, we will assume any feature is a actively growing sharp-tipped crack, just to be conservative. Because even though it may not be a crack right now, you're pretty confident it's crack-like, it may turn into a crack down the road. So then, knowing the equivalent pressure, we can look at fracture mechanics. And up here, I just put two of the more basic, simple, repetitive equations. On the left is Newman-Raju. On the right side would be API reference stress value. And this kind of models that stress loading the conditions around the crack tip. So what we're saying with the composite here is effectively we're reducing the amount of pressure that is seen at the crack tip, and we implement that by replacing your live pressure, your operating pressure, with that equivalent pressure reduction. If you do that, you can calculate out your fracture toughness loading values, you can calculate out your stress loading values at the crack tip, and you're essentially just running through your standard fracture mechanics model here now. And we did see some pictures of an FAD, a failure assessment diagram earlier. Got another one for you guys. But what we're looking at here now is we can show the effect that the composite repair has. So for example, this orange dot up here would be the unrepaired pipe at design pressure being run through those fracture mechanics equations. In this case, it's not predicted to fail at the pressure that's input. It's pretty safe, but it's close to that line. And the closer you are to the line, the more likely it is to fail. But if we put a composite on it and we reduce the stress at that crack tip, then that dot drops down to where that green dot is. And now we're a pretty safe distance away from that line. So it's just reinforcing the idea that a composite is taking away some of that stress, and it's going to make that crack tip not fail at those pressures or require higher pressures before failure is achieved. So this is just looking at static pressure conditions. And some of the things we've noticed through our testing, either the JIP or the more owner-operator driven tests, right? Our approach is way too conservative. So in a lot of cases, we may be predicting failure at 1,500 PSI, but we end up blowing out outside of the composite repair zone at 4,000 PSI or something. So this model is very conservative. There are a lot of things we need to do to make it more accurate, but my goal isn't necessarily to be accurate at the moment. It's to be consistently conservative. All right, if you're concerned about a crack possibly going bad, I can tell you with confidence, putting a composite repair on, that you can hit these pressures and it's not going to fail. That's really what I care about now, and we can worry about how conservative it is down the line as we get more testing and more information. Like I said, we are looking at some future test programs. The one we're doing with ADV and Sergio is going to help get some more valuable data that we can use to model and make changes to our tool. But the other thing to consider would be the cyclic analysis. So here, I put the Paris-Erdogan equation. There's several different equations you could use, this being the simplest. Essentially what we're doing here is, again, we're reducing the effective pressure that the pipe is seeing. And what that translates to here is in between every single cycle, the stress loads that are reached are lower. So you're lowering that delta K value. And that effectively is saying that the crack grows less per cycle. And if it grows less per cycle, you can cycle longer before that crack goes through. So we don't have any testing or examples to show you on that. A lot of it's owner-operator. I'm hoping we can get a lot more testing and predictions done in future test programs coming up soon. But what I have seen that I can't release is that, again, we are very conservative here, almost an order of magnitude in some cases. So we know the process itself works. We know that composite repairs can dramatically increase the amount of life that that crack has left. It's just, again, a discussion between accuracy and levels of conservativeness. So one thing to consider here, when you are doing cycles to failure, the discussion typically is, at what point does that crack see a stress load that causes an instant burst to failure, right? So normally you can determine how much your crack can grow until you reach that critical points. and how many cycles that takes is your life. Now, when you put a composite on top, mixed with what I was saying about the burst pressures, it's not going to burst until you have a much deeper crack. So knowing what crack depth you need to use for those equations, that's something that takes some research, and we're looking into how to better define it and have better predictions that we can release. Now, when you're doing a cyclic failure analysis, right, it's an iterative process. You in one cycle, how much does the crack grow? How much does that crack grow in the axial length? And then you have to do an assessment check to see if it hits that failure point or not. And if it doesn't, you do another cycle, and you keep doing it until you reach your end life. And there are a lot of variables, including material properties, that can make drastic changes in these equations. So knowing what your fracture toughness values are, your material property C, and whatever other variables you can come up with, it is an important step, and it's going to increase the accuracy of any of these predictions. Like I said, there are some things that are causing us to be conservative, and we are looking at future test programs that kind of help with better identifying those and making it better. But overall, the current model, the current approach is pretty simplistic. It still requires some fracture mechanics, some stress distribution modeling, but it is something that has been consistently conservative. And we feel pretty good when we're looking at a situation. We know how much a composite repair can help. And in some cases, we may identify that this is not a good candidate for a composite repair, because you may want a permanent repair, but my model says it might fail in 2 or 3 years. So you need to cut that out and replace it or something. So it at least opens up those kind of discussions on where composite can be helpful. A quick note on girth welds and SCC. These are 2 other very common types of cracks that the industry is concerned about. As it currently stands, with girth welds, the fracture mechanics modeling there works. We can do estimates, you can do FEA analysis, and we're pretty sure composite repairs can help there as well. There just isn't a current test program that has focused on cracks and girth welds. So we're not pursuing that at the moment, but if you're interested in doing that kind of testing, talk to Chris. I hear he likes testing. Additionally, same kind of story with SCC, right? There's a lot of things we think we can do with SCC. Theoretically, this should be a pretty easy one to do. It's just the number of testing that has been done here is slightly higher than 0, maybe like 1. So we just need to do a little bit more testing before we start really generating a lot of data and publishing and going after there. But if girth welds and SCC are of interest to you, let's talk. We do think composite repairs can be very valuable here as well. Last, I want to have a discussion on permanent versus temporary. And if you're looking at the B31 standards, everything has to be permanent, but they don't tell you what permanent means. So this is kind of how I view it, right? A temporary repair, it's essentially one where you have a planned replacement. That replacement might be next week. It could be 4 or 5 years from now. You just plan on replacing it when it is convenient to do so. And I really think a composite repair makes a lot of sense in these scenarios. If you find a crack and you still want to replace it, put a composite on, and it does 2 things, right? It can make that failure, a potential failure, just completely disappear. Or if it does end up failing, it changes the failure mode. It's no longer a seam wall bursting open. It's now that crack may develop and go through wall, but you now have a contained leak as opposed to a dangerous, rupture. And the other case would be permanent. So if you have a very shallow crack, if you have something that doesn't cycle very much, a gas line, put a composite repair on it, and your life prediction on that may be hundreds and hundreds of years. While not technically permanent, I think you could argue that it's a pretty permanent repair, especially if you can continue to monitor that crack and crack growth in years going by. And I do have the hope that future ILI technologies, EMAT tools, will only increase with their accuracy and being able to look at that crack as it goes down the line. So just general guidelines that I put together, probably break it more than I follow them. But temporary repairs, any cracks that are deep or crack-like features that are deep, above 50% is a good rule of thumb here. I would put those as temporary. Or if you're looking at liquid lines that have very heavily or aggressive cycling, that alone may cause it to be a temporary scenario. On the other hand, if I'm looking at a more permanent repair option, looking for cracks that aren't very deep, and I really like a gas line where it has very low cycling. It's almost always a great candidate for permanent repair scenarios. So with that, I don't know how much time I got left, but I didn't want to upset you. Okay, so 10 minutes of stand-up comedy. Now, questions, go ahead.
So, your last statement on gas lines, what about
Yeah, so what we do is if you know your cyclic parameters, you know how much it is or something like that, you know, you have a rainflow analysis, you can tell us and we can plug that information in, and it gets converted into more simplistic models, so we can plug it into that Paris-Aragon equation. So we're converting it to number of cycles translates into number of years. So yeah, if it's not a severe crack, even if it's aggressive, you may still be good for 30, 40, 50 years in those environments. It just really depends on how severe your crack is and what cycles you're looking at. We'll say we do have people that are doing repairs on liquid lines as well, so it's not completely out of the boat, it's just not always the better candidate. All right, any other questions? Not on that end. All right, thank you guys very much.
All right, thank you, Casey. All right. Well, thanks, guys. We're coming up to our last talk of the day. The last one's going to be a virtual talk by using Skow. Has Jason logged in yet?
No, but he's on his way. He's logging in.
Okay. All right. So maybe we'll break for a few minutes until he gets kind of connected. I think there was a little confusion on his end. He's in the mountain time zone up in Edmonton, so I think he was off an hour. So give him a second. If you don't mind. You want to read it off, Ashley? Oh, here it is up on the screen.
Okay.
Oh, yeah, you'll need this.
All right, so how do you calculate the number of layers to be used? Do you consider the crack growth in the repair calculations? Yep, so it really depends on how conservative you want to be. It's going to drive a big factor here. At the moment, I don't necessarily have an equation that says, you know, this crack means 17 layers or anything specific. You know, those kind of minimum layer guidances are given in the PCC2 standard just to provide a minimum. In this case, what we're really looking at, you know, it depends on the line itself, but there's two main considerations. The first being the burst pressure. We'll increase the layer count until we have that, the point in the FAD plot is significantly far away from the line where your engineers, the owner operator engineers, and us feel comfortable calling that a good repair for the burst. The other one gives us a little bit more direct layer counts in some scenarios when we consider the cyclic fatigue. Right, we can bump it up. 12 layers gives you 5 years, 18 layers gives you 23, and 24 layers gives you 106 or something. So then we can kind of start to get a reasonable thing. With a 50-year design, that could lead to a direct. That being said, with currently publicated information, most of the repairs out there that have been currently installed in the field, most of them are 24 layers, which is slightly over a quarter of an inch. And there's currently 3-foot long repairs with a crack length maximum of 3 inches. So the currently existing documentation is what supports that if you want the easy route, if you will. Although there's no reason to believe your fracture mechanics modeling and the approaches wouldn't allow larger cracks, deeper cracks, or anything like that. So there is some leeway here, but it really just comes down to, from a design perspective, what do you feel is justifiable to, pretend you have a future audit? What level of comfort do you guys have? So really, we just want to provide the documentation that provides that backup, and that's really the justification for layer counts. It's not as cut and dry as replacing external loss. Second part, I'll keep this answer shorter. So if we're looking at burst values, then crack growth doesn't play too much of a factor, but the crack growth is what is driving that cyclic fatigue model. So we're assuming at the end of the life, design life, whatever that crack depth is from cycling, that's what the first pressure has to be.
I get asked this, and I know you do too, about the permanency of repairs. You might talk a little bit about the safety factors of PCC2 and how that gives you and me confidence these things are going to last for a long time.
Yeah, so if we're talking just standard repair information on how good a composite or how long a composite repair can last, I can tell you, last week we blew up a clock spring that was in the field for 25 years and it burst outside the clock spring. So that's pretty good. We've also had the 10-year study finish up. The number, what was it? MATR 3.4. I don't memorize numbers. So we know from the fact that it's buried in the ground, there doesn't seem to be any dramatic effects on the composite itself. If we're talking more engineering based, there's two main things you want to look at. One is your creep failure. So if that composite sees high loads of stress over a long amount of time, the material can begin to creep and you could eventually get a failure. Now, PCC2 has testing designed to test exactly that. And that information is what is used in the design to make sure that scenario never happens. In practice, I would say most of the repairs that are actually put on the field, they're probably operating at about 5 to 15% of their ultimate tensile strength, which is significantly far away from the point where material creep becomes a concern for failure. The other thing to consider would be cyclic fatigue. And again, cyclic fatigue in the composite itself is based on the stress cycling that's occurring. And once again, the actual stress that happens in the composite is so low, you're really not too concerned about cyclic failure. It's more likely your pipe the defect is going to fail first from cycles. That being said, you mentioned safety factors. I think the easiest one to know is for a composite to be PCC2 compliant, it has to have a minimum strain to failure value of 1%. And if you're just going off the most basic design scenarios, you have a allowable strain limit of 0.25%. So that's already a 4-time safety factor built in. And then I think most of the equations themselves have an additional safety factor on top of that. Like I said, I think just the fact that you're operating at 5 to 15%, that tells you the level of safety factors that composites have. Talk longer if you want more time. All right.
Thank you, Kate. I'll spend some time introducing Jason. So I've known Jason for quite a while. Probably met him about 7 or so years ago. He worked for one of the larger consulting firms up in Edmonton, and probably about 3 or 4 years ago, about the same time Chris started ADB, Jason started a group called Integral Engineering. And so kind of, the theme earlier on when I kicked this off in the morning, I was talking about a lot of times we talk in the deterministic world where we're assuming, lower bound toughness, we're adding tolerances to the sizing. And so now we've had time to kind of talk about some of the work that's been done in the materials area to define the distributions better. Also, we heard from Rhett, he was describing some of the EMAT technologies. And so I thought this was a good way to end this talk. Jason's he's a statistical guru. And, the problem with that deterministic realm is you can start plotting those points on the FAD. And again, you never really know what the probability of failure is. So you're kind of, making guesses on how to react when you should be hydro testing, when you should be re-inspecting your pipeline, and those type of big decisions that operators have to make. So Jason, he's he's taken all of this data around from the materials, the flaw size, and the stress, and he's using the same models, but again, he's applying statistics and probabilities to running these, millions and millions of times, all these various combinations to determine what the true probability of failure is. And understanding that can really better prepare you to make those big decisions with your pipelines when you hydro test, and even do you need to replace the entire pipeline? So it looks like Jason's at home right there. Last time I saw him, I don't think you had a beard or anything. So you've taken advantage of COVID.
Hey, can you guys hear me over there?
All right.
All right. Can you guys hear me? Is that working out, Ryan? Good. Okay. Well, thanks a lot, Ryan. I really appreciate the opportunity to talk to you guys today. And with respect to the beard, I'm calling from up here in Canada. It's 22 degrees below zero where I'm at, and it's almost a health hazard not to have a beard if you can grow one. So it's partly COVID and partly weather related. But let me just jump right into it. I'll share my slides. I just got a note here that says go ahead and share the slides. And how's that working? Is that working for everybody? Can you see my slide? Okay, good. I just got a text back here. All right, I'm just going to carry on then. Now that I have my screen in full screen, I can't see you guys. So if you do need to contact me, just give me a text as well, as long as everything's working out. So Ryan introduced me as a statistics guru, and I hope that that's not true. And I don't like to use that term because it never bodes well when you're trying to make friends to say that you know anything about statistics. This presentation doesn't have any equations, but it does show some of the math concepts, but it shows them in graphics format. It shows you some images that represent some math that's going on, but I try not to put any actual formulas in a presentation because I don't like seeing them either. So let's get started here. I'm going to talk about three things in the next 25 minutes. The first one is the CRAC Model Consortium. This is a PRCI consortium that is a joint effort between Ted Anderson and Integral Engineering, and we're putting together a tool that evaluates the probability of failure of a crack using Ted's MAT8 model. And through that project, we're also making some improvements to the MAT8 model. So I'm going to just take a couple slides on that. Then I'm going to talk about the probability of failure for a defect. This includes a crack, but it could be applied to a corrosion as well. And then lastly, I'm going to talk about sizing error because that's one of the key inputs into a probability calculation. Sizing error basically means when you measure something, it could be bigger, it could be smaller than what you measured. We all know that. We get ILI reports and so on, and we know that the true size is something different, could be different than what's reported. So how do you deal with that? And so I've got two options for how to deal with that. So here is a summary of the CRAC Model Consortium, the first topic. And the idea is to improve the integrity management of seam weld anomalies, to be able to reduce the risk of seam weld anomalies for pipes with low toughness. Okay, sorry, I'm just checking some text here just to make sure it's working. All right. And then to reduce the cost by avoiding unnecessary digs. That's the second sub-bullet point there. Through this consortium, we're also going to compile the vintage pipe fracture toughness test data that's available from across the industry. And there's some of the operators have put significant effort into doing some very detailed tests, and that's going to be compiled. And it's number one, going to be used to resolve the equations in the MAT8 model. But also compiled for the members to be able to use for other types of fitness for service and evaluations that they're conducting. And lastly, to enable the consortium members to present a united front to regulators so that if everybody's solving this problem in a similar way, then of course it holds more weight and is also easier for the regulators to interpret.
So what are some of the improvements that we're going to be looking at for the MAT8 model? So some of you might be familiar with the PRCI MAT8 model. It was a project that Ted Anderson ran a few years back. And I think it's still just, the model is still just called PRCI MAT8 based on the track that it ran in PRCI. But it's basically the best model that we have for long seams right now. And Ted's really good at what he does. He made some improvements over the previous models that were available, including the API 579 crack model. And some of the things that he's been working on recently are realistic crack profiles. And so that would mean like a crack that's not necessarily just semi-elliptical shape. It could have kind of a river bottom, complex type of river bottom shape. The second one is predicting the sharpening of blunt seam weld flaws. One of the problems we run into when we're doing the assessment of cracks is often that we assume everything's sharp. And if you do that, then there is a low efficiency in the dig program because you end up excavating and repairing so many cracks that may not be necessarily growing or may not necessarily be sharp. So part of this is to be able to distinguish which ones need repair versus which ones that don't. And the sharpening of blunt seam weld flaws is a key element to that. And then the last bullet point there is the crack geometries that deviate from hoop stress plane. And that basically means cracks are often assumed to be semi-elliptical, but then also perfectly axial. And of course, we know things like hook cracks are not perfectly axial, so they don't do a good job of solving for that. And so this model is being extended to be able to handle those cases as well. The last one, I'm just going to jump down to the bottom of this slide, is that there's a software tool that is going to implement this in a probabilistic way. So you can, as Ryan was describing, you can calculate something in a deterministic fashion, which results in a evaluation of burst or no burst, right? It just says either your pressure's good or it's not good. So that would be a deterministic assessment. But a probabilistic assessment would result in something that says you have a 1 in 100 chance of this crack failing within 5 years, or you have a 1 in 1,000 chance, or maybe 1 in 10,000 chance. And so now you're talking about probabilities. And when it comes to predicting the future, it's really always a probability. There's nothing deterministic that can ever be solved that way. And often companies will identify risks and consequences and have a corporate risk matrix that helps them decide what risks they're willing to expose themselves to. Those require a probability. So if you wanted to use those same types of corporate management tools to manage integrity, then you do have to come up with a probability. And this is the way to do it. The last bullet point here says uses cloud computing to speed up the calculation time. So why is that? The reason for that is that some of these calculations, they have to do the same thing kind of over and over and over again. And they can take quite a bit of time, even with modern computers. When we've built this on the cloud, what we do is we access 10,000 computers or CPUs at once to solve the problem. And the result can come back in, let's say, 10 or 20 minutes, when if you had your home computer crunching away at this, it might take a week or 5 days or something like that to solve it. And because we can use the cloud, we can just access these CPUs when we need them. We can turn them off when we don't need them. And it can be just a very quick calculation. Here are some of the examples of that realistic crack front and the planar and off-planar shapes. You can see on the bottom right, it's showing a blunt crack that over time starts to get sharp and will start to grow again. So these are the types of improvements that are being made to the MAT8 model in this project. This next slide here is an example of the user interface of the software that uses the cloud. And I'm not going to go into this. I just wanted to show this. You can see on the bottom right, there's kind of a cloud of points. What that represents is some of the simulated calculations that are being done. And the points that are below the blue line and below the red line represent higher probabilities. So I'm not going to dive into that in too much detail, but just to show a simple idea of here's an interface. You can put in some properties like wall thickness, yield strength, and so on. And then on the right, a burst capacity calculation is being done using that cloud computing that I was talking about. Okay, so often when I talk about this, people say, well, how do you get a probability from a single defect? How does that work? So I've got a little animation here that's hopefully going to help answer that question. So let's just think about the axes here and the one data point that I have on the screen. Along the y-axis, I have defect length. Along the x-axis, I have defect depth. And so there's a point that's a measured point, and you could think of this as, let's say, coming back from your ILI tool. It's in your ILI report. This is not the whole report. This is just going to be one feature that comes back in your ILI report. So how do we get a probability out of that? Well, here's some of the things that we need to know. For example, if we go deep enough, we're just going to cross wall thickness. And if we do that, then, of course, that crack could grow to some point where it turns into a leak, right? Secondly, we could have some geometry that results in a burst. So we know if it's very short and it gets really deep, that would probably result in a leak. But if it starts to get longer, it might result in a burst. So this is representing that case. Now, if that black point that I've drawn on there, if it grows up and crosses into the red zone, it would fail by burst. But if it grows straight to the right and crosses over the wall thickness barrier, then it would turn into a leak. So that's one of the things that we're going to be looking for. Now, when you measure a point, the depth and the length from the ILI tool, we recognize that the ILI tool may have some error associated with it. So that blue curve at the bottom is representing the range of sizes that the depth might actually be compared to what was reported in your ILI report. We know we have the one measurement in our ILI report, but if you went out to the field and you could verify it in detail with a highly accurate device, you might find it's a bit bigger or it's a bit shallower than what is called. Similarly, you could have the same thing for length. It's calling a specific length, but it might be a little bit longer, it might be a little bit shorter. So what do those two distributions mean? They really mean that we don't know the exact geometry perfectly. We have an indication of what it is. One way to represent that would be to show kind of a cloud of points like you see on the screen now. The cloud of points represents possible cases that could exist given that we have that measurement of that one point. Now you would notice that as you get further away from that center point, it's possible that it's way deeper and way longer than reported, but not very likely. So, you know, having something that's much deeper and much longer than what was called in your ILI report, you know, might have a 1 in 100 or 1 in 1,000 chance, whereas only slightly bigger or slightly shallower could be quite common. It might happen, you know, 20% of the time or something like that. So that's what that cloud's representing. Now, of course, none of those potential gray points cross the leak line or the burst line, but that's in the present day. And we know that it's actually not failing right now as we're reading the ILI report. What we're concerned about is what's going to happen next month or next year or in 5 years. So in that case, we're trying to account for growth. So if you could imagine growth in this plot, what would that look like? Let's say it grows like that. It grew mostly in depth and a little bit in length. And so it kind of went more to the right, a little bit up. And now what we see is that some of those potential sizes are crossing over into the leak and crossing over into the burst. So what does that mean in terms of our probability? Well, if I highlight the ones that cross the line, and then I take the ratio of the ones that are colored brown compared to all of them, that's your probability of failure. It's as simple as that. That's what probability of failure from a single point actually means. The second thing we can talk about is, what are these lines anyway? And now what I've done there is I've made them wider. And the reason for that is when we talk about when does a feature burst, we have a burst model telling us that that's the case, but the burst model isn't itself exactly precise and exactly correct for all cases. In fact, if you go and look at the lab data that was used to generate the model, you'll often see that there's quite a bit of scatter in that data. And so if we try to account for that scatter, I'm going to draw that like a thicker line rather than just saying it's a precise line and as soon as you cross the line, it's for sure a burst. I'm going to say, well, some of the time you have to go a little bit further in to become a burst. And some of the time when you get close to it, you're on that thicker part, that's also a burst. And that's going to be a probabilistic relationship as well. So if I highlight my points, I don't know if you could see the difference there, but I've just changed some of the colors that are either the brown, darker brown color or the gray color. And really your probability of failure now is simply the ratio of the number of points that are colored brown compared to all of the points that you've simulated. And each one of those points is going to be a simulation. Okay, so that's probability of failure. Let's talk about sizing error. So that was the distribution that we saw, the little blue curve that was kind of on the bottom x-axis and on the y-axis, and that was representing how good is our measurement. So this is a pretty important input into the calculation. So when we're looking at sizing error, what are we talking about? Well, we want the sizing error, we want the ILI and the measured size to be on that 45-degree line. If it's on that 45-degree line, it means we've done a good job. ILI and true size are aligned, so you'd see something like this. Now we know that data sets never are this clean. They don't look like this. So what would happen is, sorry, that was just an example showing that they're both exactly the same values. But let's say the slope is not exactly 1. Let's say it's a little bit shallower. And what this would mean is that you tend to undercall large features and overcall small features. That would be expressed in this equation to the right as a slope. Yeah, sorry, I said there was no equations. I guess there's one equation here, but it's just the linear equation. So let's say we have the slope that's a little bit shallower. We might actually have a bias, so that pushes the line down like that, and that's represented by that beta over there. Now, we also might have scatter, which is represented by this error term. It's that E in the equation to the right. And then to make things even more complicated than that, we would say, well, there is a lower bound under which the ILI tool is not reporting anything, because that would be close to the noise threshold of the measuring tool itself. So those points do not show up in our data set. And then we end up getting something like this that we have to use to assess how good was the measurement. On top of this, you can take any individual point and you can say, just like we did before, that both the measured size, which would be, let's say, a field measurement, and then the ILI size both have error. And so that could be represented as a cloud of points. Every other point might have some similar characteristics. The cloud doesn't have to be the same size if it's not the same accuracies of measurement for each one. So you might have something like that. And really what we're trying to do is we're trying to come up with a bound of how good is this tool at telling us what we really want to know, which is the size of the feature that's there. So this is a complicated process, as you can see, but of course it's not impossible. We have some rules of thumb. So let me go through what some of those would be. This is a plot, a unity plot that is representing what is done in the API 1163. And this is called a level 2 assessment, where you get the specification from the ILI vendor and you report it. You report the features on a unity plot, and then you put this blue band, and anything inside the band is considered within tolerance, and anything outside the band is considered out of tolerance. The out of tolerance plots are highlighted with these oval shapes. And the way this is calculated is if that oval shape crosses or touches that unity line, then it's considered a good measurement. But if it doesn't touch it, it's considered an out of tolerance measurement. And that's why we have these colored red compared to the blue ones, which are inside. This will allow you to do a null hypothesis test on the vendor specification, which results in either rejecting or not rejecting the specification. If you don't reject the specification, then basically for all of the calculations that Ryan was mentioning at the beginning of the presentation, for all the calculations you do for burst pressure and so on, you would just use the vendor specification because you did this test and you found it's probably good. An alternative to that is to take the data you have and then calculate the performance, and that's what's shown on the right. This would be referred to as a level 3 assessment by the recommended practice 1163. And in the past, 1163 referred to level 3, and they simply stated that it could be done, but they didn't say how. In the most current version, they have 2 examples of how it could be done. And one of the examples is the case that I'm showing you here on the right, where you have the data and then you're hypothesizing how good was my measurement given that I have this data set. And then you can come up with your own confidence bounds, which are those blue lines, the darker blue lines on top and bottom. The way you would use this is you would say, if my ILI measures something that was 2.5, my guess from this performance would be that the true size lies somewhere between 0.9 and 3.7. So it's very similar to how you'd use a vendor specification, except this is now calculated using your own data from your inline inspection report and your excavation plan. The way this particular model works is that it produces regression lines that could describe the data that we have. And those are the light blue lines in the middle. And really what it's doing is it's saying that given the points that we have, the measurements we have, each of those blue lines is a potential model that solves for that performance. But every time you run the simulation, you get a different line. That's why a bunch of them are plotted here. And from that group of lines, you can produce confidence bounds, which is the darker lines at the top and bottom. The other thing that's interesting about this particular model is that you can see the distribution gets wider over time. This could be the case. It's sometimes referred to as trumpeting. It means that as the flaw gets bigger, the error or the scatter in the measurement also gets bigger. It doesn't have to be the case. And the way this would calculate if it's not the case is those blue lines would be just perfectly parallel rather than kind of spreading out as you see here. Okay, the last thing I was going to go through, this is actually just more of a fun concept. So I covered the three main concepts. The first one was the PRCI consortium project. The second one was how do you get probability from a single defect? And then the third one was measurement errors. So this one is more for fun. And unfortunately, since I'm not hearing any feedback, I don't think we could do anything interacting on this. So I'll just kind of go through it and you guys can think through what you think the answer would be. The problem here is a statistician named Abraham Wald was working for the military. And you can see those red dots on the plane. Those are bullet holes in planes that would come back. And he was charged with the problem of how do we add armor to our planes so that they can last longer in battle and sort of resist being taken down in battle. And so this is the type of information he had. And the question was, where do we put the armor? Because we can't just make the whole plane much more resistant to bullets because it's too heavy. So we have to be very selective about what we do. So he had these types of data sets. So here's kind of an example. The fuselage had 1.7 bullets per square foot. The engines had 1.1 bullets per square foot. And then sort of the rest of the body had about 1.8 bullets per square foot. So the question is, well, if you're going to put armor on the planes, where do you put it? And the answer is that you put it where there's fewer bullets because the planes that came back had fewer bullets in those locations, which allowed them to come back. So if you want to beef up the protection, the armor of the planes, you would put it in those locations, not the locations that had the most bullet holes. And so that was the theory he came up with, and it was a pretty good practical type of thinking. So that's exactly what they ended up doing. And finally, I'll leave you with this plot, which is for statistical purposes, the difference between a normal distribution and a paranormal distribution.
All right. The folks that are left here. Yeah. Are there any questions online at the moment?
Nobody here?
All right, we'll let Chris ask his question then. Eric, can you do this?
Just so everybody can get it. Hey, Jason, great job. So I guess the question I got for you is you're obviously working with a lot of different people. Are you doing work with some of the ILI companies? I mean, they're obviously generating the largest number of data. And kind of going forward, in the next 2 to 5 years, how do you see this, prolific generation of data that we're getting? How are you going to be using that to help the operators, better predict the future performance of the pipe?
Yeah, good question. I think there was a couple of parts there. The first one on working with vendors, and for the most part, my work is with operators, and I work with vendors, sort of in conjunction on projects for operators. I haven't been doing a lot of work directly, let's say, for ILI vendors or measurement technology vendors, although the same stuff applies both ways. With respect to the mass of data that's sort of coming online, I mean, what we have here is an amazing opportunity to improve the industry. We have a conglomeration of a bunch of, I would say, timely events that are in our favor, and we have to take advantage of them. So one of them is the democratization of the CPU, which is what we're using with this cloud computing. Like I was saying, getting access to 10,000 CPUs and then solving a problem. That's available to everybody at this point. The idea that the infrastructure in the ground is getting older and we have to do a better job of maintaining it. So we have to use sort of better science and better numbers. That's kind of timely as well. And the advancement of algorithms and machine learning and even artificial intelligence, which has to be used correctly. Obviously, it's actually a big pit sometimes. It doesn't help you, but if we use it correctly, there's a lot to be gained. So what I would see with these large data sets coming online is, number one, we have an amazing opportunity to improve what we're doing and how we're doing it. We have an amazing opportunity to be able to do probabilistic calculations and really calculate the things we care about. What we care about is failure. We don't care about a burst pressure safety factor. That's not what we care about. It's not what companies care about. It's not what the public cares about. They care about the likelihood of the event that we don't want either happening or not happening. And that's really how we should manage it. So we're going to go more towards that. When we talk about big data sets, it is a huge advantage, although there's a caution there, which is low quality data doesn't help us as much as it sounds like it would. If you have 50,000 data points and they're all low quality, we can't get as much out of that as we can if it's 100 data points that are extremely good quality. So the lab work that is precise, it's maybe more expensive per data point, but that is always going to be the gold standard no matter what. And we're never going to be able to move away from that. So it's a mixed bag. There's a huge, huge opportunity, but we have to be cautious and we have to use the right tools.
Any more questions for Jason? Yeah. All right, Jason. I don't think we have any questions right now for you. Looks like maybe Sergio has a quick comment about your beard.
All right.
Well, really good talk, Jason. We really appreciate you joining. I always find your talks very engaging. So with that, I think that brings us to the end of our time here. I appreciate everyone joining today. Probably sometime next week, I think we were talking about sending out a survey just to get your idea for future events. Our plan here at ADV is to every quarter we were discussing holding a similar type of event and focus on different aspects of pipeline technology. So sometime in March, April timeframe, we plan to have another one of these events around inspections. That'll be the focus of the next IDT Expo. So, we'd like to get some feedback and kind of, what day of the week works best for you. How this is really the first time we've really done this full-scale live stream stuff where we had presenters working virtually. And so we'd like some comments to help us out, prepare for the next one. But besides that, are there any kind of final comments anyone has? Okay. Well, thank you, guys.